Hello, my name is Chad Smith, and I'd like to welcome you to my course, AWS Certified Security Specialty Complete Video Course. AWS certifications are among the most sought after in the technology sector, and the certification exams cover a wide range of services, technologies, and implementation patterns. The Security Specialty Certification is not an entry-level exam, and the questions reflect the difficulty required to fully test the holistic knowledge of AWS security professionals. This course targets the certification exam and will provide directed study of the exam topics in several helpful ways. First, it will cover the exam logistics and detail the background knowledge needed to pass. This material will include both general security topics and specific AWS offerings and architectures. Next, the course will explain all 5 question domains with examples, diagrams, and case studies from real-world applications to help with knowledge retention. Finally, the lessons covering exam content contain sample exam questions that will be dissected with answer strategies explained in detail. It is important to know why the correct answer is correct, but it is also important to know why the incorrect answers are incorrect. This knowledge improves the ability to narrow the field of answers when guessing is required. During the past several years, I have spent an increasing amount of time focused on cloud security. As an AWS architect and experienced system administrator, I use real-world situations and decisions made in the trenches to illustrate the concepts covered by this certification. I've always been fascinated and excited by the evolution of security in AWS, and I will focus that energy on the exam materials and strategies to maximize your chances of achieving the certification. Module 1 consists of a single lesson, which introduces the Security Specialty Certification. It will detail the prerequisites and skills required to be a successful candidate for certification. Welcome to Lesson 1. In this lesson, we will introduce the concept of security in AWS and how it relates to general security skills. We will go over the scope of the course material and finish with a discussion on the technical skills required by AWS for exam candidates. The concept that is represented in this quote has a familiar application in a number of different topics. When you're a kid and your parents ask you to do your chores, and you get them all done for a month straight, and then you miss one, it's that one that gets you in trouble. From an IT operations standpoint, if you're responsible for updating all of the SSL certs for your company, and you do it just fantastic for several years, it's the one you miss that impacts the CEO while he's in the middle of giving a demonstration. And so it applies to security. It takes 20 years to build a reputation and a few minutes of a single cyber incident to ruin it. AWS takes the topic of security very seriously. And if you go to the AWS main webpage where they define the term, the acronym itself stands for Amazon Web Services, and then they provide a little bit of a description. And there are a lot of different words that they could have used. Performant, cost-effective, resilient, but no. They chose to use the one word secure as the first word to describe the platform. Amazon Web Services is a secure cloud services platform, offering compute power, database storage, content delivery, and other functionality to help businesses scale and grow. Anyone can go to the AWS certification portal for the Security Specialty certification and read through the exam logistics, how to register, and how to get a refund if you decide you aren't able to take your scheduled version of the exam. But I'd like to talk to you a little bit more about some of the other numbers. And let's just walk through these one at a time. The number of questions on the exam are 65, and we're going to go into detail on the question domains and how many questions they represent in the exam, but 65 questions is a lot. And by the time you reach the end, you might be experiencing some fatigue. 170. This is how long, in terms of minutes, that you have to actually take and complete the exam. Again, this might sound like a lot of time. It's almost 3 hours. But those 65 questions are not necessarily written as a couple of sentences with one-word answers. And so 170 minutes starts to feel like a very short period by the time you get near the end. 4 to 6. These are the number of answer choices that you're going to have on each of the questions. Some of the questions might have answers that are shorter, simple phrases, maybe one sentence. But there are other questions where each answer, and there might be 6 of them, could involve multiple sentences leading up to an entire paragraph. 750 out of 1,000. This represents the new scoring paradigm that AWS has applied to several other certifications. And it means that it's going to be less transparent to you as the test taker how you did exactly in each of the question domains. And in fact, you're not going to be told how many points each question is worth. That is something that Amazon keeps private. On your exam, there will be a number of questions that are not scored. And it doesn't matter if you got them right or not. It's not going to have any bearing on whether or not you achieve certification. 0. That's the penalty for guessing. You want to make sure that you have answered all 65 questions on your exam so that you can maximize your chances of achieving the certification. I'd also like to walk through some test-taking strategies that I've learned over the years and that I feel apply very well in the context of this certification. I feel like you should take 3 passes through the questions. The first pass is where you take care of the low-hanging fruit. These are the questions where upon reading, you get a few sentences in, you realize you already know the answer, and you don't even have to look through all of the answer choices. Once you find that answer, you know it's right, you move on. Go through all 65 questions, find the low-hanging fruit, and answer them. Your second pass will be for the questions that had more question text, more answer text, because these are going to take a little bit more of your time and concentration. They might not be difficult topics, but they take longer as far as the amount of time you have to finish the exam. And finally, your third pass are going to be for the questions where you're guessing. And it may be that on that first or second pass, you saw the question and you thought you might know the answer, but then when looking through the answer choices, you realized you had no idea. The reason why you save these for the third pass is that by going through the other questions twice, there might be a hint or an association that helps you go back and look at these questions where you didn't have any idea, and maybe after 2 passes through, you now know how to answer them so that you're not completely guessing. The question domains for this exam are pretty simple and straightforward, and the representation on the exam are going to be pretty widely varied. The first of these is incident response, and it really doesn't account for many questions. If you're looking at 65 questions, this is only going to be 6 or 7 questions total of the exam. You have logging and monitoring. This is a topic that quite a number of AWS professionals are pretty familiar with. Infrastructure security. This is going to represent the largest percentage of questions across the entire exam. But counterintuitive it may seem, you probably don't want to spend all of your time studying here because, again, this is where a lot of AWS professionals spend the majority of their time. They already know these topics. The final couple question domains are where the really deep, complicated information comes in. Identity and access management and data protection. These are the areas where this certification gets more complicated and goes deeper than any of the other certifications do, and it's for this reason I recommend you focus your study time on these two question domains. I'd like to set the tone for the rest of our material by discussing really quickly what is going to be covered, the question domains for the certification itself. We're going to go through sample questions where you can get an example of what some of the exam questions might actually look like. We're going to talk about answer strategies, both in context of the sample questions and just in general. We're going to talk about key terms and buzzwords. There are certain terms that you can look for in the questions that will help you identify which of the question domains that question belongs to. We're going to talk about different options for the security services and features that are part of the AWS ecosystem. And to summarize what is in scope for this content, it is strategies for achieving certification. So I'd also like to talk about what is not going to be covered as part of the material. This is not an introduction to AWS. The certification itself has a lot of advanced topics that if you are just now learning about services and features as part of the AWS ecosystem, it might not be for you. We're not going to talk about common service basics. EC2, S3, VPC, these are concepts that you should already be familiar with before going through this material. We're not going to talk about architecture strategies. The well-architected framework has a lot of documentation out there, and there are a lot of great examples of how to achieve it, but we're not going to be covering security in the context of resilience or cost effectiveness because that's not in scope for the exam either. We're not going to talk about operational details. How to get the work done is also documented in extraordinary detail all across the AWS website. And so, learning how to be an AWS security professional is not in scope for this course. When you go to the AWS portal for this particular certification, the Security Specialty Exam, there are a number of details that are on that page and in the exam guide that are going to look a lot like a job description, where you can envision a company who's looking for a security professional in AWS. They're going to need to ask for certain existing skills for the successful candidate. And I'd like to walk through these one at a time because you can gain a lot of information for your exam study strategies from these sentences. And the first of them is, a successful candidate should have an understanding of specialized data classifications and AWS data protection mechanisms. This is going to be one of the general security concepts that anyone who has been a security professional should already be familiar with. What you need to do for this certification is knowing how to differentiate between public information and differing degrees of private information and how they apply to the various services in the AWS ecosystem. Next is an understanding of data encryption methods and the AWS mechanisms to implement them. This is going to be pretty important because it means you need to understand at a fairly deep level what data encryption at rest looks like and the different ways to achieve that in AWS. The next skill is an understanding of secure internet protocols and AWS mechanisms to implement them. This is going to be pretty straightforward. This is data encryption in transit, and it's usually going to come down to SSL, TLS, or some kind of VPN. The next skill is a working knowledge of how to implement AWS security services and features to provide a secure production environment. And for this one, I'd like to highlight one word: working. You can't just read documentation and memorize your way to certification for this particular exam. There is prior experience that AWS recommends you have before digging into this particular cert, because the exam material is going to assume that you have general security knowledge, general IT knowledge, and the specific knowledge within AWS from having implemented these things on your own. The next skill is competency gained from 2 or more years of production deployment experience using AWS security services and features. This is going to build upon that last skill and reinforce the fact that you need the hands-on experience. There really isn't any substitute for it. And whether it's working in your personal account or doing it in a work context, gaining that experience and doing it over and over is going to be far more valuable than simply reading a bunch of documentation on the AWS website. The next skill is the ability to make trade-off decisions with regard to cost, security, and deployment complexity given a set of application requirements. This particular skill means you should also be an AWS architect, and that you should understand the principles that go along with architecting infrastructures in AWS. The well-architected framework is going to come in very valuable here, but you want to recognize that this isn't going to be a primary focus of the exam. It is just a skill set that AWS assumes you already have. The next skill is going to be more based on operations, an understanding of security operations and risk. And so this is going to require some prior experience, some prior understanding of SysOps principles, and when to recognize that you've reached a point where you're secure enough and that going further is going to either introduce greater complexity, greater cost, and in essence, provide diminishing returns. And I'd like to finish up with a couple of themes that you're going to see all throughout the content over the next several lessons. The first of these themes is going to be based on the word prevention, the act of stopping something from happening or arising. This is taken straight from the dictionary, and you probably already know applying this to a security topic means you're going to be figuring out how to avoid an event from happening in the first place. How can you prepare? The next theme is going to be recognition, which is just the acknowledgement of something's existence. Now, in the context of security, it's going to be a security event. How do you recognize that it is currently happening within your environment? And the third theme is mitigation, the act of reducing the severity, seriousness, or painfulness of something. And again, this is going to be a security event, which can be very painful, but how do you fix it? How do you stop the bleeding? And as we're going to find out coming up soon, that this is actually a continuum. It's not just 3 separate topics. Module 2 is the first discussion of the official exam content and will be a single lesson. It will cover the first of the 5 question domains called incident response. In Lesson 2, we will cover the topic of incident response. This is also a general security concept, and we will discuss some general principles as well as specific strategies for preventing, recognizing, and mitigating security incidents. The case study for Lesson 2 will walk through a security event consisting of a compromised EC2 instance. This first question domain is a fantastic way to introduce the concept of security in terms of the certification. And the main points for this question domain are: first, given an AWS abuse notice, evaluate the suspected compromised instance or exposed access keys. Verify that the incident response plan includes relevant AWS services. And evaluate the configuration of automated alerting and execute possible remediation of security-related incidents and emerging issues. Between these 3 points, they don't go into a lot of detail. They do require a lot of broad knowledge that you will be applying, but the detail is going to be seen in the final 4 question domains. So let's start with the abuse notice. If your account has a suspected compromise either at the key level or at the EC2 level, AWS will send an email with some details around that suspected compromise activity. From a customer perspective, it is up to you to then evaluate that compromised resource, such as an EC2 instance, to see if you can figure out whether or not you are truly being subject to a security event. And this is a service we're going to be talking about a lot. There's a feature called VPC flow logs that allows you to view the incoming and outgoing traffic at different contexts. You can isolate your resource from the network using features like security groups. And you can even launch a replacement using backups in the form of an AMI. If it is an access key that has been compromised, you have different strategies for mitigating this. You can look at the Access Advisor reports to determine which services have been accessed using that key and at what time. You can look at guard duty, as mentioned in the previous slide. You can look at your CloudTrail logs. These are going to provide a full audit trail of everything that's happening in your AWS account. And you can take action in the form of disabling keys or creating new keys that replicate the functionality. Every good security professional should already recognize the term incident response and recognize that an incident response plan, as a general security concept, is going to have some specific utility within AWS. And so for this question domain, I'd like to refer to an official source for discussing what it means to build an incident response plan. And we're going to go straight to the NIST that has a number of different documents that are available for general security professionals. But this particular document is named the Computer Security Incident Handling Guide. And in this guide, there are a series of events and actions that comprise the incident response lifecycle. And as you can see, the first 3 elements of this lifecycle correspond to the themes that we've already introduced. We have number 1, preparation. That leads into detection and analysis, which then is followed by containment, eradication, and recovery, but possibly used in a cycle with detection and analysis. And finally, we have post-incident activity, which is really just a mixture of sections 3 and going back to section 1, preparation. The first section of the incident response lifecycle is preparation. And within preparation, there are a number of different tasks that you're going to want to know about from a certification perspective. And we're going to start with limiting the blast radius. And for this particular step, there are a couple of different concepts that are pretty straightforward and that you can associate with this. First of these is deploying your accounts using AWS organizations. We're going to spend quite a bit of time talking about all of these concepts later in the course. The intent is to introduce them as part of this question domain. Next is to deploy your networks using multiple VPCs. Both of these can help you when there is a security event and you need to restrict the amount of resources that the actor can possibly have access to. Next is self-documenting infrastructure, and AWS gives you a couple of different ways to go about this. There are different services and features that can help you document your infrastructure without having to explicitly open a text editor. First of these is AWS Config. This is great from an inventory perspective. CloudFormation, where you're actually defining infrastructure elements using text files and then creating them from those text files. And third, AWS SSM. The Systems Manager service gives you a number of features for inventorying at a deeper level, including network information, installed software, and license usage. The next step is creating procedures and runbooks. This is really not specific to AWS, but there are a couple of ways that you can apply this to certification. And the giant icon of S3 is here for a reason. You need a place to store these documents, and if you're placing them in the same account that you're trying to protect, you're not exerting all of the effort possible. What about making sure that your documents are highly available, that they're stored in a resilient way where they can't be deleted? S3 is a great example of a service that can help you do this within AWS. And you might want to recognize too that storing all of your documents in the cloud are not going to help you if it is the cloud provider themselves who end up being compromised. And so the idea of keeping a thumb drive in a safe with all of your documentation is a valid option. Our next task is to generate a normal behavior baseline, and AWS provides a couple of ways to make this happen. The first of these is pretty straightforward, just using the monitoring service called CloudWatch. We're going to be referring to this constantly throughout the course. Anytime monitoring is mentioned, chances are good that CloudWatch is going to be part of the conversation. Guard Duty is another service that's going to be recurring all throughout our content from a security perspective because of its ability to identify on your behalf when it suspects that abnormal behavior is happening in your account. Next, clean images for restoration and recovery. This is definitely a proactive step, and there's a number of ways to make sure that this is going to be a possibility for you if you experience a security event. The most obvious way to do this is by creating AMIs of your EC2 instances. AMIs themselves include snapshots, but if all you need is a backup of a data drive, then a snapshot is perfectly appropriate. You can store file-based backups in S3. You can store configuration files in S3. And finally, you can store licenses or keys using services like SSM Parameter Store or even the AWS Secrets Manager. The next task is going to be assessing risk. And for this, we have 3 specific services that are going to be very helpful to the AWS customer. The first of these is Amazon Inspector. This is going to help you from an EC2 instance OS perspective. Next, we have Guard Duty. And as you can see, this particular service has already been mentioned in several of these tasks. It is an important service for you to learn from a certification perspective. And we have Amazon Macie. This is a service that can help you assess whether or not permissions on S3 buckets are too permissive. Next, we have network security, and we're going to be dedicating almost an entire lesson to this coming up. There are a number of different features that you can use to help improve the security from a network perspective. You can use network access control lists, security groups. Both of these are going to be part of the VPC context and used together. You can create VPC flow logs for auditing the network traffic flow within a VPC. And finally, you can use the AWS Web Application Firewall service. This is used in conjunction with CloudFront and applies to web traffic where you have the ability to identify and potentially drop abnormal requests. Our next step is the ability to store relevant event information. This is absolutely a proactive step that should be done as part of your strategic planning for security in AWS. And there are a range of features that you can use here as well. CloudWatch logs is a great way to store log files durably with excellent ways of accessing them for analysis purposes. You have AWS config streams where you can create snapshots of the metadata configuration for your resources. You can use CloudWatch events to keep track of what's happening in your AWS account. You can store access logs in S3 in addition to CloudWatch logs. And you can use CloudTrail logs that are stored in either CloudWatch logs or S3 to help correlate between behavior and actions that were taken to create that behavior. Detection and analysis is the second step in your incident response plan. And like the first step, is going to have a number of subtasks that you're going to want to learn about from a certification perspective. The first of these is recognizing signs of an intrusion attempt. And as you've probably guessed, we're going to see some familiar services and features. Services like CloudWatch are clearly going to be used for monitoring across a lot of different areas and is a great way to recognize when your infrastructure is being attacked. CloudTrail gives you the audit log of everything that's happening in your account from an API perspective. We have our good friend GuardDuty who's making a reappearance, and VPC flow logs. All of these can help you to recognize when a security event is taking place. Next, we have incident analysis. And this is where we start to get a little bit more complicated in terms of the tasks that you might be performing. In order to be able to analyze what's happening, you need to have a performance baseline so that you can recognize when you are experiencing abnormal behavior. And in order to do this, you can create dashboards in CloudWatch that are specific from a security perspective. You can use SSM Insights dashboard, which allows you to bring in graphs and data from a lot of different services and even across regions. You need to be able to understand normal behavior. And I can't emphasize enough that understanding normal behavior does not just apply to applications, but it also applies to the account itself. And the GuardDuty dashboard is one way to help accomplish this without having to put any overt effort into it. Within incident analysis, you can also implement log retention. This is going to help you with the forensics and making sure that you have all the information at your fingertips that allows you to perform the analysis. For this, you can create CloudWatch logs expiration. You can work with S3 lifecycle policies and even Glacier Vault Lock policies to make sure that your log files are always present in the service or feature where you expect them to be. You should be able to correlate events between logs and metrics. This is a more sophisticated behavior of monitoring, where you're not just looking at numbers and latencies and connection attempts, but being able to determine when your application is experiencing certain metric value changes, can you go back and look at the logs to find out why exactly that is? And for this, you can use services like Amazon Elasticsearch with a Kibana dashboard. This is going to be similar to Splunk. You can use CloudWatch Logs Insights, which is a great way for on-demand searching of the logs that are being stored in that CloudWatch Logs service. You need to be able to send notifications when an incident is in progress or has been detected. For this, we have a couple of different services. First of these is SNS, Simple Notification Service, just a topic and subscriber service where your notifications can be sent to a number of different subscribers, and it doesn't just have to be email. If all you need is email, you have SES, Simple Email Service, to accomplish this. And a third element would be the Trusted Advisor. You can sign up with a couple of email addresses, and when AWS recognizes that a security event is taking place, this is where they will send those notifications. You should take advantage of any and all help resources that are available to you in AWS. If you suspect that your account is being subject to a security event, open a support case right away. AWS has professionals who are dedicated to identifying, analyzing, and mitigating security events. You can search the AWS forums. It's possible that you're not the only customer whose account or resources are under attack. And this makes a great case for signing up for premium support and building that relationship with the AWS support team so that you already have those resources ready and available when you experience that security event. The third piece of your incident recovery plan is going to be containment, eradication, and recovery. And much like the previous two steps, we have a number of subtasks that can be applied in an AWS context to help you deal with a security incident. The first of these is your containment strategy. And this is not something that you should be figuring out on the fly. The word strategy should be your clue that this is going to require some planning and forethought. Much like the other subtasks that we've discussed, AWS provides a number of services and features that can help you with containment, such as security group rules, the ability to revoke IAM sessions, the ability to create WAF ACL rules on the fly, your IAM policies and the ability to apply extra policies or to apply restrictions to existing policies, the ability to rotate your access keys, and finally, when you're working with encrypting your data at rest, the ability to rotate the backing keys for KMS. Next is going to be evidence gathering and handling. And there are a number of different ways to make this happen, and you're going to start to see our familiar players showing up again from the previous steps. We have the CloudTrail audit logs. We have CloudWatch logs, which could be access logs, execution logs, or security logs. We've got our VPC flow logs with a full accounting of the network traffic, whether it's been rejected or accepted. And we have tools like the IAM Access Advisor, where you can determine whether or not a user or a particular set of keys have been used for abnormal purposes. The next step is to identify the attacking entity. And for this, we have a couple of familiar features. We have DNS lookup using services like Route 53. This is not specific to AWS. This is going to be a standard strategy for associating host names and domains with IP addresses. And we have guard duty, which is starting to sound like a broken record. Your next step, eradication of the potentially compromised resources. And there are so many different ways that this can be accomplished. There are a couple of examples I'd like to provide, like simply terminating the instance that has been compromised. You can disable compromised keys, or segregate compromised data and resources for analysis later, with the ability to recreate them so that you're not losing functionality with your applications. Now we can start to move into recovery steps. And for this, I'd like to start with some terms that should be familiar. Recovery time objective, recovery point objective. Both of these are common in context of disaster recovery and business continuity. You need to recognize how much time you have to be able to recover and how much data you can afford to lose in the meantime. You need to recognize which resources need to be repaired in line and which can simply be replaced outright. And for all of this, you should be thinking about how automation can be applied. This is going to require a combination of skills, both in architecture and in operations. And now we move into the cleanup phase. The first thing we should be looking to do is remove any temporary resources that were created as part of our mitigation process. We should do a full KMS key audit to make sure that there isn't any other compromised resources. We can do a full IAM audit as well to make sure that all of our IAM resources have their permissions restricted to the appropriate levels. And we need to review all of our findings to make sure that we're able to recommend the appropriate steps that will help us go back into preparation. The final step in our incident response plan is going to be how we apply everything we've learned and turn it into preparation for the next event. And we can start with the lessons learned. And there are a number of different ways that we can implement this in AWS. First of these is going to be evidence retention. How do we hold on to the forensic data that we gathered in such a way that it doesn't compromise the rest of our account? We can use S3 buckets for this. We can use Glacier. We could create AMIs of compromised instances or snapshots of compromised volumes. And we could even then share these or copy these to other accounts where we could perform further experiments. The next step is going to be our proposals for improvement. What did we learn and how can we turn that into a more secure infrastructure going forward? We might be able to make proposals in terms of permissions. How can we improve our least privilege implementation across the board, whether it is user-based permissions or resource-based permissions? We can look at access control there, network permissions. Both of these are going to help in terms of restricting a potential actor's ability to view data that they shouldn't be able to view. The next thing we can do is improve our monitoring by creating better dashboards or by taking prior passive responses and turn that into active responses with automated mitigation. For the first of this course's case studies, we're going to put that incident response plan into action with a scenario that is based around one of your EC2 instances being compromised by some unknown actor. And so what we're going to do is we're going to walk through this real-world experience and determine how can we identify the compromised resources. Where do we go to figure out the blast radius for this event? How can we actually mitigate? How can we solve the problem? And how can we recover safely while making sure that we've retained the forensic data so that we can use that to go forward and improve the overall security of our AWS resources? And so we're going to start with our first option where we don't have a lot of monitoring in place. AWS is sending us the notification over email. This is the abuse notice. And when this happens, there are going to be a lot of questions, clearly from our side. The who, what, when, where, why, and we're not really going to have a lot of details. We have very few data points. We have no context. that's not optimal. There's got to be a better way to figure out that our resources have been compromised rather than waiting for AWS to send us an email hoping that we're actually going to read it. And so this better way is going to be through proactive work on our part. We would have existing monitoring in place using services like CloudWatch, VPC flow logs, or even having firewalls installed and security software on the EC2 instance itself. This is going to allow us to gather data points on the security performance of our systems. And by doing this, we can start to correlate our viewed behavior with actions that are being taken potentially by an outside source. And that allows us to make informed decisions as to how to move ahead. So as far as figuring out the blast radius, we have the AWS ecosystem with services and features that can help us. If we think we have a compromised instance, we need to know the different types of resources that are associated with the instance. AWS Config can provide this for us in a graphical or a text format. So what are we going to learn? We'll learn that our EC2 instance is associated with a subnet, and that has a network access control list attached. We're going to be able to see the security group that is associated with our instance, EBS volumes that are associated with the instance, and as we learn this information, it might actually change the scope of our suspected compromise. Our next step is to mitigate the event. And one way to go about this is to contain the compromised resource. If you look at this as an EC2 instance that's associated with a security group, and let's say that our instance is part of an application server fleet. And if we look at the security group rules, we can see that for this particular application, we allow inbound ICMP from anywhere in the VPC. We allow inbound TCP on port 22 from our Bastion security group for SSH purposes. And we allow inbound TCP port 8080 for application traffic being sent straight from the load balancer. Our security group outbound rules have nothing present. We took the guidance from AWS and removed the default outbound rule that allows all outbound traffic because our application is self-contained. So what can we do to help contain this resource and make sure that there's no possibility of further exploration of the environment happening? Well, we can create another security group. We call this containment. And for this security group, we allow no inbound traffic, no outbound traffic. The question is, how do we apply this to the existing resource? Well, it's pretty simple. Through the dashboard or through the CLI, we can actually detach the existing application security group from the network interface of the instance itself and attach our new containment security group to the instance in its place. And by doing this, our net effect is that the instance is now completely isolated from the network. Once we have assurance that that compromised instance cannot do any further damage, now it becomes a matter of recovering. And the first step of recovery will be to restore our capacity while retaining the forensic data. And so one way we might do this is to just leave the isolated resources in place for further analysis. And assuming that we have created our backups, our fully usable images for this application, we can then simply launch another resource to replace that capacity that is placed into the correct application security group. And now we are able to service the same amount of end users that we were before. We also need to retain our forensic data. And one great way to do this is to persist all of our logs and data points in some kind of durable storage so that we can do our post-mortem without having lost any of this information. We can do this from our CloudWatch logs, our VPC flow logs, our EC2 instances, and whether we're sending these logs directly to CloudWatch logs or directly to S3, or have some kind of copy in place to make sure they end up in a persistent data storage, it is important to make sure we retain this information. Once we have the information, and we'd like to be able to analyze it, our goal is to gain insights so that we can make recommendations. And so, in order to make this happen, there needs to be some middle ground between the storage and those insights. One way to do this is by using Redshift queries. By using the feature called Redshift Spectrum, we can query S3 data as if it were part of a Postgres database. We can query the data directly in S3 without using Redshift. We can just use the service called Athena. We could perform jobs that require code to be executed using AWS Glue. Or we could even look at the data directly using QuickSight, which is more of a graphical interface for us to be able to explore this data as if it were in a database. Now, our final step is to take our recommendations and turn those into action. And so what kind of actions might we expect to see that we can turn into preparation to improve our security? How about more restrictive security group rules? If we find that an old rule was left in place and that is what our attackers use to get in. We can turn this into better monitoring, looking at different metrics, having more alarms, maybe creating active responses so that we're not reacting when the event occurs. Welcome to the first of our question breakdowns for this course. And the way this works is we will read through the question. We're then going to highlight key terms so that you can recognize and associate those terms with this question domain. And then we're going to look through all of the answer choices to determine which one is correct. We're also going to talk about why the incorrect ones are incorrect, because that can be a really important tool when you're taking the certification exam when it comes to narrowing down your options. For this question, your security team has been informed that one of your IAM username password pairs has been published to social media and has been used several times by unauthorized sources. How can the security team stop the unauthorized access, determine what actions were taken with the compromised account with minimal impact on existing account resources? So the first thing we're going to do is we're going to highlight a bunch of these words because they're going to help you determine not only the question domain, but what types of services or features you might expect to see in the correct answer choice. And for this question, we're definitely going to be talking about IAM. And then it's a matter of making sure we can meet our three requirements. Stop unauthorized access, determine what actions were taken, and make sure our solution has minimal impact on the existing account resources. And so we'll look through these answers one at a time, starting with A. Immediately change the IAM user password, ask the user what actions they would normally take, and then compare that with their current AWS inventory. Well, this does stop the usage of the IAM account, but it doesn't really address the actions that are taken with the compromised credentials. We would need some kind of audit trail to be able to determine that for sure. So let's look at B. Delete the IAM user account, remove all resources created by the user, and then analyze the CloudTrail logs for unauthorized actions. Well, this too stops the usage of the IAM account. It does allow you to analyze the unauthorized usage, but it is going to impact existing resources, and so this is not going to be a correct answer either. Let's look at C. Immediately change the IAM user password and remove all resources created by the user. This sounds like a pretty extreme solution, and guess what? It's not correct. It also stops the usage of the IAM account, but it's absolutely going to impact existing resources if you're deleting all of them. Now, once you make it to this point, you've got a pretty good idea that D is going to be the correct answer, regardless of the wording. But let's go through it anyway. Immediately change the IAM user password and analyze CloudTrail logs for unauthorized actions. This gives us the ability to stop the bleeding. We stop the usage of the IAM account, and we've analyzed and created a list of actions that were taken by the unauthorized actor, and we did not impact existing resources. And so the correct answer for this question will be D. Module 3 consists of 2 lessons, collectively covering the second exam question domain called logging and monitoring. This broad topic will be split into Lesson 3, Security Monitoring, and Lesson 4, Logging Solutions. Lesson 3 will go over different security monitoring options in AWS. These options include infrastructure, application, and account security, as well as troubleshooting steps. The case study for Lesson 3 will walk through a broken monitoring situation, including how to troubleshoot and repair the configuration. In this question domain, we have 4 points to cover. Design and implement security monitoring and alerting. Troubleshoot that same security monitoring and alerting. Design and implement a logging solution, and then troubleshoot logging solutions. And AWS will definitely be asking you questions on troubleshooting. So when you see these question domains that have troubleshooting as a main point, you are going to need to learn how to troubleshoot the topics that are discussed as part of that question domain. And so we're going to start with some of the basic services and features for monitoring infrastructure security. The first of these are VPC flow logs. A VPC flow log, functionally, is just the ability to capture and audit all of the header information for the network packets that are being passed through different contexts. One of these contexts can be a specific network interface inside of your VPC. Another possible context would be an entire subnet. If you enable a VPC flow log on a subnet, you do want to understand that it will only audit traffic that is attempting to enter or leave the subnet. It does not capture any of the header information for traffic that is sent between 2 nodes within that subnet. The third context is the entire VPC. And one thing that's nice about this particular feature is that you can just enable it on the whole VPC and go back through CloudWatch Logs Insights or some other analytical tool and dig through and find the stuff that you need, knowing that you captured everything. But if for cost reasons or complexity reasons it doesn't make sense, you can still deploy at that network interface or subnet context without worrying about capturing everything. Next up, for monitoring the security of your infrastructure is GuardDuty. And this is a service that creates machine learning models to help determine what normal behavior looks like so that it can recognize abnormal behavior. And so what does GuardDuty actually look at to build these models? It looks at CloudTrail logs, it looks at VPC flow logs, and it looks at DNS logs. Now, one of the coolest parts about GuardDuty, you don't have to have any of these enabled. All of that information is being generated and captured automatically, and services like GuardDuty will take advantage of that, even if you don't want to have to pay for enabling VPC flow logs at entire VPC contexts. The next way for monitoring our infrastructure security will be just through straight operating system logs. If we're deploying EC2 instances in fleets and singleton instances and other types of services, then we can install and configure the CloudWatch agent and forward all of our operating system logs to different places like S3 and then perform Athena queries on them. We can send those logs to CloudWatch logs and then use the Insights dashboard. Or we can even use third-party products like Splunk. The certification does take into account that we are technology professionals. And there will be questions that assume that you understand technologies that are outside of the specific AWS ecosystem. Our next service for monitoring infrastructure security would be AWS Config Rules. And this is where you create a stream of configuration changes and then you apply logic to that stream to determine if a change matches the rule. And so what types of things can you capture? Security group changes is a great example. A new instance launch that doesn't meet certain criteria, or even changes or additions to existing route tables. Any of these might indicate a security event has occurred and you might need to take appropriate action. Next, we have Amazon Inspector. And this is a service that focuses specifically on EC2 operating system vulnerabilities. And the way this works is by installing an agent, determining a rule set that you would like to execute on the instance, and then actually running the job. And so it can locate vulnerable operating system libraries. Maybe you have a version of OpenSSL that was not updated properly. It can identify unencrypted network traffic. If you're performing communication on port 80 and you're not using SSL or TLS, that is the type of thing that Inspector might generate as a finding. Inspector will also look at all listeners on your instance and over a period of time determine which of them are not being used and pass that along to you as a finding. So now that we've discussed a little bit about the infrastructure security, let's talk a little bit about how to monitor the application level security. And for this, one of the flagship features of AWS is going to be CloudWatch logs. This is one of the best places to aggregate text-based information with the ability to analyze and take action based on what you find. And so what types of services and features are actually going to push logs into CloudWatch logs? Well, first off, anytime a Lambda function executes, anything that is generated as output or log is going to go to CloudWatch logs. If you've installed that CloudWatch agent that we talked about in the previous section, and you're already sending operating system logs, why not send your application logs to CloudWatch logs as well? And if you've moved away from the OS entirely, but you're not using Lambda, you're using some kind of container, the service Elastic Container Service or Elastic Kubernetes Service, both of these give you the ability to push your container logs directly into CloudWatch logs. There are other application activities that happen within the context of AWS that may not generate an application-specific log. And for these, if you've implemented Cognito user authentication that we're going to talk about later in the course, then it generates logs whenever somebody logs in. These go straight to CloudTrail. If you're utilizing step functions for workflow orchestration, as your work passes between steps, the logs are sent to CloudTrail. And if you're taking advantage of some of the services in AWS that are focused more on DevOps, like code deploy, a code deployment is logged and sent to CloudTrail, not to any of the other services. And when you think about log storage in AWS, S3 is probably one of the first services that comes to mind. And there are services that send their logs directly here. If you're working with an elastic load balancer, the access logs are sent directly to S3. If you've enabled CloudFront access logging, these too are sent to S3. And let's look at a little bit different use case. What if you want to keep track of your Redshift queries? All the queries that have been executed against your database are stored in an audit log and kept in S3 as well. So we've discussed a little bit about infrastructure security monitoring and application security monitoring. What about monitoring the account itself? Your AWS account is going to be one of the most important places to concentrate your monitoring activity. And it's not good enough to just keep an audit log. And so we're going to take advantage of one of the features of CloudWatch called CloudWatch Events. This is different than CloudWatch Logs. You can think of this as sort of an event bus where activities can be published, and then you can create rules to match specific events and take action accordingly. Guard duty makes a reoccurrence here. When guard duty generates a finding based on unauthorized or abnormal behavior, those findings can be sent directly to CloudWatch events. CloudTrail can generate events that are sent to this CloudWatch event bus in addition to sending the actual log to CloudWatch Logs. And even AWS Organizations, which is a service that allows you to collect multiple accounts and manage them much like you would a directory, generates events, and these events are sent to CloudWatch events. Another way to monitor what is happening with your account separate from those CloudWatch events are AWS config rules. And one advantage to using config rules is that there are a number of predefined rules that you can take advantage of. You just have to activate them. One of these is determining whether or not CloudTrail is enabled on your account. If it isn't, it becomes non-compliant with this rule and generates a notification. You can use a config rule to determine if your IAM keys have been rotated on an appropriate schedule. You can even use a predefined config rule to determine whether or not MFA is enabled on the root user of your account. And if it ever becomes disabled, again, send a notification. And this leaves a lot of room for automation to be put into place, where you do more than just send a notification, you actually mitigate the problem. When it comes to the topic of security monitoring and troubleshooting when it's not working, what we're really doing is we're just troubleshooting monitoring itself. There really aren't a lot of specific security issues that arise in the context of monitoring that you wouldn't see just by deploying a lot of different monitoring across AWS. But there are a couple of scenarios that you might want to watch for on the exam. The first of these is a scenario where it describes a security event that was possibly mislabeled as a performance event, such as an auto-scaled group of EC2 instances suddenly have CPU spikes. And the automated mitigation, because it's auto-scaling, is to simply scale out the fleet. But what if it was a security event? That might be a scenario that you might get on the exam. Or describing how to identify and mitigate vulnerable libraries that have been located on your EC2 instances. There are some different tools that you can use for troubleshooting that you might also see in the context of the exam. Amazon inspector findings are very important. This is going to be the outcome of the rule sets that are executed on your EC2 instances. CloudWatch alarms and metrics. This is a pretty obvious answer, but it applies in security as well. CloudTrail logs. These are going to be super important because a lot of security events are difficult to identify by metrics alone. They require some kind of correlation with log files that have been generated. And you have the ability to generate on-demand queries to look through these CloudWatch logs inline in real time using CloudWatch Logs insights. There are a number of different root causes that you might expect to see within this question domain as far as troubleshooting the monitoring implementation. It might be that there were unclear requirements for security monitoring in the first place, or maybe the team was told, just figure it out. Poorly implemented CloudWatch alarms. CloudWatch alarms are surprisingly complicated, and it is a good idea for a security professional to understand how CloudWatch alarms deal with certain factors like missing data points. And the final root cause example might be that there are gaps in your operating system update procedures and compliance checking that have left some services exposed with a higher risk. Welcome to the case study for this lesson. In this one, we're going to talk a little bit about what happens when monitoring does not do what it was designed to do. And for the specific scenario, it's that we had a recent security event. It never generated notifications. And so we have to go through and troubleshoot to determine what happened and then try and fix it. And so our tasks that have been set before us are to trace why notifications have not been received, implement the missing monitoring, and to ensure compliance going forward. So for the first step, tracing why notifications never happened, we're going to take an example notification and monitoring pipeline that goes from CloudTrail through CloudWatch logs and using CloudWatch alarms, sending notifications through SNS to an internal email address. And it's our job to look at this pipeline and the services involved and locate potential points of issue that if we have misconfiguration or some other event, that the notification would never be received. And so we'll start right at the beginning with CloudTrail. If CloudTrail is disabled, we are no longer generating the audit logs, and the rest of the pipeline is completely irrelevant. Let's move a little further. What about CloudWatch? If the CloudWatch alarm has been deleted or modified, maybe one of the time periods was changed so that the CloudWatch alarm will never actually fire. Let's keep moving to SNS. What happens if the topic or the subscription to the topic has been deleted? Well, clearly no notifications are going to happen. There's another possible root cause here. If your account sends a huge burst of traffic through an SNS topic to email address subscribers, AWS might view that as a potential security event on their end, and in that case, AWS will actually remove all of your subscriptions and set them to a pending state so that no more emails get sent. And the reason for this is that AWS does not want to be found by some outside body to be the source of spam or other kinds of email that would put them on a blacklist. And so their automated mitigation strategy is to remove all of the subscriptions to the topic and recreate them and put them in a pending state so that you must reconfirm. And our final root cause might be that the email distribution list or the email address that is the destination for this notification may have been deleted or changed, or the email was otherwise blocked at the client side. What happens if you have used an individual's email as a destination and they leave the company? They might still be getting notifications, but you're not going to be taking action because nobody's actually reading them. Let's look at our next step. How do we implement missing monitoring depending on where we found our root cause to be located? If we start back at the beginning of the pipeline, if CloudTrail is disabled, well, we re-enable it globally. That will mitigate the immediate issue. What if the problem happened in CloudWatch? Document all of the alarms that should be there and recreate anything that is missing. From an SNS perspective, if you have to recreate the topic or the subscription, that can be a good short-term solution. If the root cause was that AWS throttled SNS for you and already recreated all your subscriptions in a pending state, you might have to notify AWS that the problem has been solved on your end so that they will enable your ability to send email again. And finally, if you have these email notifications going to an individual, it's strongly recommended that you send them to a distribution list instead. Even if only one person is subscribed internally, that reduces the risk of an employee leaving the company and these notifications being dropped on the floor. Our third task is to ensure compliance going forward. How do we make sure that if this happens again, that we're able to automatically mitigate to return it to a known correct state? If we go back to the beginning of our pipeline and look at CloudTrail, we can set up an AWS config rule plus a Lambda function. The config rule will recognize that CloudTrail has been disabled and trigger a Lambda function that re-enables CloudTrail. A potentially high-value target for anyone attempting to break into your account would be to make sure that CloudTrail is disabled so there is no audit log going forward of any of the actions that take place after that. If you have automated mitigation in place so that CloudTrail is re-enabled immediately, that limits their ability to damage your infrastructure. Next, let's talk about CloudWatch alarms. You could create a scheduled Lambda function that runs on a regular basis, every hour, every day, every week, that evaluates all of the existing alarms and recreates the critical ones as needed. Applying compliance at these first two layers, though, are really just reactive measures. Setting up code that will re-enable, recreate, resubscribe, it's reactive. We can do better than that. We can be proactive. We could, through the use of permissions, prevent an SNS topic from being deleted or prevent subscriptions being deleted. And we can apply that to the entire account using an AWS organization's service control policy. A good organization that is security conscious is probably going to be implementing a combination of proactive and reactive mitigation. As long as you are looking for automation first, rather than relying on individuals to get their hands on a keyboard or a mouse to fix the problem, you're moving in the right direction. Welcome to the question breakdown for Lesson 3. And for this question, I wanted to provide a scenario based on the ability to monitor applications running on EC2 and the complexities that can arise from applying multiple requirements. An application running in EC2 has a requirement for independent, periodic security checks against the application code. These checks can send notifications upon reaching their warning threshold, but for critical alerts, they must shut down the application on the instance. How can your security team perform these checks without injecting code into the application while meeting the notification and active response requirement? So let's look at our key terms. This question has quite a bit more of them than our first question breakdown in the previous lesson. We have the EC2 service that has clearly been identified. We have the independent periodic security checks against the application code. This implies a number of complexities. We have to deal with notifications and an active response that actually shuts down the application on the instance. And so our ability to do that is also dependent on not injecting code into the application itself. And so let's look at our answers. We have 4 choices, A, B, C, and D, for this particular question, and each of these have multiple sentences that can help us determine whether or not the answer choice meets all of our requirements. Let's look at A first. Install the AWS Inspector agent on the instance and schedule regular audit jobs. Send the findings to an SNS topic with a Lambda function subscribed that parses the findings and responds appropriately. This one hits all the right buzzwords, right? You have Inspector, which is going to be looking at your operating system. You have integration with other services, an SNS topic, and a Lambda function to automatically send notifications or shut down the application. This seems like a great answer. However, AWS Inspector can't audit your custom application code. It can only look at existing operating system libraries. But sending the findings to Lambda is a good option anyway. It just doesn't answer the question appropriately. So let's look at B. Deploy a second application on the EC2 instance with the security audit code. Send security audit results to CloudWatch events and create a rule to send warning events to SNS and critical events to SSM run command to stop the application. This too sounds like a fairly complete and correct solution. And it does actually meet all of the requirements for the question, including the independent audit. That is extremely important, and that's why we deploy a second application on the instance. So if we think we have it right, we still need to look at answers C and D. And for C, install the CloudWatch logs agent on the instance, streaming all application logs. Create a CloudWatch logs metric filter with alarms for notification and a Lambda function to stop the application. This doesn't act as an independent audit. It relies on application logs being generated for its actions. So let's look at D. Install the inspector agent on the instance and schedule regular audit jobs. Uh-oh, we're in trouble already. We already have an incorrect answer that had similar text. Send the findings to CloudWatch events and create a rule to send warning events to SNS and critical events to SSM run command to stop the application. So we have a mixture of implementation tactics taking from an incorrect answer A and the correct answer B. And so Inspector still can't audit custom code. The passive active response mechanism mentioned in the second half of the answer is appropriate, but it does not meet all of the requirements. And so our correct answer is going to be B. Lesson 4 details different types of logs in AWS and how to monitor them. The logs discussed are access, execution, and security logs. After that, we'll go over a number of log processing solutions, as there are many of these in AWS. The case study for this lesson will be a scenario for automated log management. If your IT infrastructure is taking web requests from any clients from any locations, chances are you're generating access logs. And when you generate access logs, it becomes really important to monitor them, both from a performance standpoint, but also from a security standpoint. There are a number of services in AWS that generate access logs, and it's in your best interest to know how those access logs can be stored and what permissions mechanism is used to do so. We'll start with the API Gateway. This is a service that was released along with Lambda functions, and they were designed to be used together. The API Gateway writes all of its access logs directly to CloudWatch logs as an optional feature. And in order to make this happen, you have to configure an IAM role to allow API Gateway to communicate with CloudWatch logs. CloudFront can also be used to generate access logs. And with this service, it's a little bit more primitive with the access control and the locations. It does use S3 only. You don't get a choice as to whether or not you'd like to put it into CloudWatch logs. And it only uses a bucket ACL to place those logs in the bucket. The Elastic Load Balancer also uses S3, like CloudFront, but it uses a bucket policy. And so the mechanism that you learned about by deploying CloudFront access logs into S3 really doesn't apply to the Elastic Load Balancer. And there's another note that I'd like to make on this one. You see the asterisk on the slide, best effort delivery. If you dig deep enough into the documentation for access logs from an Elastic Load Balancer, you'll find that AWS does not guarantee that every single log entry will actually make it into the S3 bucket. And from a security perspective, this might be important enough that your organization chooses to store access logs from some other tier instead. Now, the final service for access logs is S3. You can enable an S3 bucket to act as a static website, and when you do so, it uses similar mechanisms to CloudFront to store its access logs, using another S3 bucket and a bucket ACL. But, much like the Elastic Load Balancer, an S3 bucket access log mechanism is a best effort delivery. Execution logs are another important way to monitor the security of requests that are passing through your application infrastructure. And there are a number of services within the AWS ecosystem that generate execution logs. The first of these, if you remember from the previous section, also generates access logs. But where API Gateway access logs are optional, the execution logs are the default. And, like the access logs, they are written directly to CloudWatch logs using an IAM role. Lambda functions also generate execution logs, and for each Lambda function, it's going to log every output, whether it is info or debug or some kind of error condition. It's going to be logged and sent directly to CloudWatch logs using an IAM role. If you have custom applications that are running on EC2 instances, you can set up the CloudWatch agent or the CloudWatch logs agent, or custom scripts to send your logs directly to an S3 bucket using an IAM role, or to CloudWatch logs using a different IAM role or the same IAM role with added privileges. After setting up security monitoring for your access logs and your execution logs, you can't forget about security logs. These are going to be logs that are generated by services in AWS that act in a security context. And the first of these is Amazon Inspector. Inspector findings are actually stored directly in the Inspector service. It acts as a storage layer for those findings. But you also have an opportunity to send those findings directly to an SNS topic using an IAM role. GuardDuty is another service that allows you to store the findings in the service itself if you don't choose to do anything else with them. Storing your logs directly in GuardDuty, however, does not give you any opportunity to provide any kind of notifications or active or passive mitigation. And so you can also choose to send your GuardDuty findings to CloudWatch events via an IAM role, where you can then set up CloudWatch event rules to match specific findings and take action. CloudTrail is the primary security audit service of AWS. This is the service that you're going to want to have enabled on every account. And with CloudTrail, you also have choices about where those logs are going to be stored. And you can optionally place them in CloudWatch logs using an IAM role, but the default is to place them in an S3 bucket. And when you enable CloudTrail, you must choose an S3 bucket to place those logs. And finally, VPC flow logs. We've discussed these a number of times up to this point in the course. A VPC flow log is just the header information for the network traffic for a particular context, whether it is a network interface or a subnet or an entire VPC. And similar to CloudTrail logs, you have a choice with VPC flow logs to place them directly into CloudWatch logs or into an S3 bucket. There are so many different ways to process logs in AWS. I've chosen examples that I feel are common enough that they may actually show up on the certification exam, but this is by no means an exhaustive list. The first of these is Amazon Kinesis data streams. Now, with a data stream, it does require that you have one or more producers that are generating log-based data, and these are placed into the data stream using a push mechanism from the producers, and then pulled from the stream using consumers running some sort of code and a Kinesis client library. Similar to the Kinesis data stream is Kinesis Firehose. And with a Kinesis Firehose, you have multiple options for analyzing or modifying the data while it is in the service. The Kinesis Analytics tool gives you the ability to execute SQL queries on the information as it passes through the Firehose. And you have the ability to actually transform the records using a Firehose source record transformation that can be used to execute a Lambda function. Now, you have multiple options for destinations for your Kinesis Firehose. You can place those records directly into S3. You can insert them into a Redshift database. You can place them into an Elasticsearch instance, or through that source record transformation, you could actually place those records in an outside service, such as Splunk. Now, let's go the other direction and assume that your data is already in storage and you'd like to perform some kind of operations or analysis upon it. AWS Athena gives you the ability to query data that is at rest in an S3 bucket. Redshift Spectrum gives you a similar ability, but using the Redshift service. AWS Glue is a little bit different. This is going to work on multiple data sources that might be in one or more accounts and give you the ability to perform ETL jobs and other analytics and create a data catalog that you can then use for performing other queries or gaining insights. EMR, or Elastic MapReduce, is one of the most common services that you should have in your toolkit for performing analytics on large data sets. It is just a managed service for Hadoop, and it can use an S3 bucket as a source for a data, and then simply place the data in the same or another S3 bucket when you're done with it. Elasticsearch is another really cool solution because it gives you the opportunity to front it with a Kibana dashboard. And there are some built-in integration points with the rest of AWS, including Kinesis Firehose and CloudWatch log groups. And these can be placed directly into an Elasticsearch instance and then queried directly from that Kibana dashboard using a browser. CloudWatch Logs Insights gives you another way for querying your data where it sits currently in a service like CloudWatch Logs. And because you can place your data in CloudWatch Logs from a number of other services in AWS or from custom applications, this can be a one-stop shop for analyzing all of your log data, and you have the benefit of direct integration to create CloudWatch alarms where you can then take direct action or send notifications. AWS Lambda is a sort of Swiss Army knife that you can use for a lot of different types of analytics. And because it has direct integration points with services like Kinesis Firehose using the source record transformation, You can use S3 event notifications or even execute the Lambda function directly from custom code and scripts. This gives you the ability to perform any kind of arbitrary analytics that might not be perfectly suited to another service. When deploying different log-based infrastructures in AWS, you'll find that you're going to have requirements for both storage of the logs and for expiration of those logs. How long are they supposed to last in storage? And so for this case study, we're going to walk through a scenario where you have to persist all of your logs in S3 and expire all entries in CloudWatch log groups after 365 days. And so we're going to walk through two different pieces of this scenario: transferring logs from CloudWatch logs to S3 and implementing automated log expiration across all log groups. So the first of these is just getting our logs into S3 in the first place. And as our logs are placed into CloudWatch logs, there are a number of ways that we can transfer them to S3, but we're going to go with a solution that utilizes Kinesis Firehose, placing the log entries into an S3 bucket. Now, anytime you are integrating services in AWS within your account, you're going to require two different elements. You're going to require permissions, and you're going to require configuration. And so let's start with the permissions portion. Anytime you create an IAM role in AWS, you're going to have to create both a trust policy and a permissions policy. The first IAM role that you're going to require for this infrastructure is one that allows Kinesis Firehose to write to an S3 bucket. And so the trust policy for this first IAM role is going to allow use by Kinesis Firehose directly. The permissions policy will allow writes to the specific S3 bucket that we've chosen to persist our logs. And now we move on to the configuration portion. This is where we create the Firehose delivery stream that is going to use the IAM role Amazon Resource Name, or ARN, from our previous step, and the ARN from the S3 bucket that we've already created. When you create a Firehose delivery stream, it's not instantaneous. It does take several minutes to provision, and so you'll want to wait until this is done before you begin the next step. And for this next step, we're going to create another IAM role. This second IAM role will have a trust policy allowing use by CloudWatch logs. The permissions policy that is applied to this IAM role will allow access to the Kinesis Firehose delivery stream that we just created in the previous step. And now that the permissions are in place, we can move on to the configuration. Now, we create a subscription filter for this CloudWatch log group using the IAM role ARN that we created in the previous step and the Kinesis Firehose delivery stream Amazon Resource Name. And what's interesting about this step is that it's not possible to do this from the console. You do have to use the CLI to make this happen. And so there's going to be a prereq to make sure that you have the CLI installed and configured before you begin this particular process. But once you've reached this point, you now have a functioning pipeline, and for the bonus round, you can use Kinesis Analytics on any of that data that's going through the Firehose delivery stream. And you can execute SQL queries on that data for analysis, or you could even perform source record transformation with a Lambda function if you wanted to determine whether or not the logs should actually be placed in S3 or not. For the second half of our scenario, we need to implement automated log expiration on any CloudWatch log group whenever it's created. And for this, we're going to take advantage of three different services. First, CloudWatch events. Second, AWS Lambda. And third, the CloudWatch log service itself. Now, in order to make this work, we're going to require permissions and configuration. And so we'll start with permissions. We're going to create an IAM role with a trust policy that allows it to be assumed by a Lambda function. The permissions policy will allow it to modify the configuration of a CloudWatch log group. After this, we actually create our Lambda function that will set the expiration days on a CloudWatch log group that is passed to this Lambda function when it's triggered as a parameter. For the other portion of this implementation, we have to create a CloudWatch events rule that will match new CloudWatch log group creation from CloudTrail. So it's going to look at CloudTrail events, but it will only match activities that correspond to the creation of a new CloudWatch log group. We then add the Lambda function as a target for this CloudWatch events rule. And note, for this part of the implementation, it does not require explicit permissions to trigger the Lambda function. Welcome to our question breakdown for Lesson 4. And for this, I wanted to choose a question that required a little bit of knowledge of operations in addition to the security strategies. So let's read through the question, locate our key terms, and then we'll look at the answer choices. You've been asked to stream application logs from CloudWatch logs to Splunk. There is an existing subscription filter on the log group set up for Kinesis Firehose to S3. What is the most appropriate way to ingest the logs in near real time for Splunk analysis? Now, as we look at our key terms, there are a number of services that are going to stand out for us. CloudWatch logs, Splunk, Kinesis Firehose, S3, but there are some other words that we need to take into account, such as near real time, and that there is an existing subscription filter on the log group already. And so as we go through our answer choices, we want to keep these key terms in mind. And let's look at A first. Create a Lambda function, subscribe to the CloudWatch log group that streams log entries to the Splunk endpoint. This sounds like a great option, right? Well, CloudWatch log groups only support one subscription filter at a time. And this is a great example of where, having actually done the work with your own fingers, your own keyboard, your own account, it's easier to learn things like this than to simply memorize documentation. So this answer isn't going to be correct. Let's look at B. Create a Splunk connector to the S3 bucket destination for the Kinesis Firehose. Well, if we do this, the S3 ingestion is not going to be near real time because the Kinesis Firehose uses a buffer and batch mechanism to place those objects into S3. How about C? Enable source record transformation on the Kinesis Firehose. Create a Lambda function using the Splunk blueprints which decompresses the log entries and pushes to Splunk. This sounds like a pretty good option too. And it does actually meet all of our requirements. It addresses the fact that there is an existing subscription filter, and it allows for near real-time streaming because as the log entries are placed into the Kinesis Firehose, they will be pushed directly to the Splunk endpoint. And let's look at our final answer. Write a shell script that uses the AWS CLI to export logs from the CloudWatch log group and ingest into Splunk. This might be functional, but it's not going to be reliable. It's going to require persistent compute resources to execute that CLI on a regular basis, and it's not going to be near real time either. And so our answer to this question is going to be C. In Module 4, we have 2 lessons covering the third exam question domain, infrastructure security. Lesson 5 explains securing AWS from global and regional perspectives. And Lesson 6 goes through host-based security and troubleshooting issues. Lesson 5 will start with edge security, detailing the different ways to interact with resources in AWS. After that, we'll cover different types of network security through the use of one VPC and multiple VPCs, in one account, and multiple accounts. The case study for Lesson 5 is an implementation scenario with multiple network security requirements. For this lesson, we're going to cover the first half of the question domain. There is simply so much material that is part of infrastructure security that it was easier to split it up into two separate pieces. And so for this first discussion, we're going to cover the first point, design edge security on AWS, and design and implement a secure network infrastructure. Now let's start off with edge security. There are a number of different ways that traffic can enter your infrastructure in AWS. And we're going to be walking through these ingress points from both perspectives of global and regional and the services that are available for each. And so from a global perspective, there's really only one service that is the primary entry point, and that's going to be CloudFront. And when you create a CloudFront distribution and you cache assets, they are going to be stored in edge locations that are data centers where AWS is not necessarily the primary owner and operator. And so you want to keep track of the data classification for the type of assets that you're going to be caching and determine whether or not it is appropriate for caching in edge locations. There are options for compute resources to act upon those assets as well. Using the Lambda at Edge feature, you can perform logic based on code at these edge locations as well. You can implement other logic on the requests themselves by using the Web Application Firewall feature, which allows you to filter the traffic according to rules that you define. Now, once the traffic makes it through this global service scope, then it's going to enter a regional service scope. And there are multiple entry points within a region for this traffic. You can store your static assets in an S3 bucket and serve them directly or behind a CloudFront distribution. You can allow access to your assets using the API Gateway service for RESTful interfaces. You can use the Elastic Load Balancer to distribute traffic to back-end resources, and the AWS Service API endpoints are also hosted at a regional scope. In this section, we're going to discuss the security features that you can use within a single VPC. And we're going to be talking about features you're already familiar with, but we're going to be correlating them with the security topic specifically. And let's start with subnets. How can you apply subnets in a security context? Well, subnets can be used to help isolate workloads. You can apply network access control lists and route tables on a per subnet basis, which means you have flexibility to create workload-specific security within that subnet. It gives you finer granularity for CIDR-related security features than simply applying rules to an entire VPC network. And you have the option of monitoring your subnet traffic using VPC flow logs. The next feature is the network access control list. And these are just stateless firewalls with ordered rule sets for both inbound and outbound traffic that is going to be applied at the subnet boundary. And so from a security perspective, you can use NACLs to deny outbound traffic to unauthorized internet destinations, as an example. You can use them to enforce compliance for application tier traffic. If you want to enforce the one-directional flow of traffic through your infrastructure, network access control lists can assist with this. You can use them for rejection as well. But it's not just about allowing traffic, you can also use them for rejection. Rejecting inbound traffic to database subnets from non-application sources. Or even preventing compromised instances from exploring their network surroundings by blocking outbound traffic on non-standard ports. Route tables are another mechanism that you can use to help isolate your workloads and manage the direction of traffic. Now with route tables, you can use them to enable features like internet accessibility. Because route tables are applied on a per subnet basis, you can use them to provide blanket access to the internet. But if you want to get more specific, you can limit that outbound access to specific CIDR ranges all the way down to a /32, which would indicate a single IP address. And with that ability to restrict that access to single IPs or smaller network ranges, this is going to allow you to implement least privilege access to on-premises networks, for example, or to enable traffic flow only to authorized endpoints. Now the final feature is the security group, and this, as opposed to the network access control list, is a stateful firewall. It also allows for inbound and outbound rules, but they're not ordered, and because they're stateful, you only have to create rules in one direction, which makes them simpler to manage than network access control lists. With a security group, you can implement least privilege because by default, traffic is blocked. And so you can whitelist appropriate external sources for access to an elastic load balancer. You could create inbound rules that allow traffic only from specific upstream sources, like an application security group only allowing inbound traffic from an elastic load balancer. For a database security group, it might be a good idea to remove the default outbound rule that allows all traffic to flow, because database services, especially if they're managed, should never initiate outbound traffic on their own. And security groups can be applied to other features like Lambda functions and endpoints so that you can apply your least privilege access by CIDR or security group membership. In our previous section, we talked about security for traffic that is already inside the VPC. Now we need to talk about traffic that would like to leave the VPC and the different egress points that you can implement and how you can apply security principles to these egress points. And we're going to start out with the Internet Gateway. The Internet Gateway is a virtual device that is fault tolerant, highly available, automatically scaled, and entirely a black box as far as the customer is concerned. You aren't given access to any of the performance or any other kind of configuration for an internet gateway except to create one and attach it to your VPC. The purpose of an internet gateway is to enable internet access, but it does not have any blacklist capability. There's no specific security features that are applied to the internet gateway itself. And so, if you want to implement least privilege while still allowing outbound access to the internet, you might want to implement more specific route table entries so that access doesn't simply go to the entire internet. And if you don't have a hard requirement for internet access, you might want to consider not implementing an internet gateway and avoiding its use entirely. And so if you still need to get traffic outside of your VPC, you're going to have to be aware of the other mechanisms to make this happen. Let's talk about the virtual private gateway. This is a device that you can attach to your VPC and is used both by VPN connections and by Direct Connect. It can be used to route traffic to and from multiple customer networks if you want to implement a VPN Cloud Hub, and it has no native features for blacklisting or whitelisting traffic. So much like the Internet Gateway, it doesn't exist in a security group. Network access control lists do not apply to it, but it can be the target for route table entries. The next egress point is a VPC peering connection. This gives you the ability to connect two VPCs together and treat them as if they were part of the same network. So from a security perspective, it does require you to implement route table entries, And if you want to implement least privilege, then you will want to take into account which services, which IP addresses that you want to be accessing in the remote VPC, and maybe limit those route table entries to those subnets or those IP addresses. The VPC peering connection also requires that security groups and network access control lists be permissive enough to allow the traffic to flow. And so you'll want to apply both blacklist and whitelist strategies to this traffic. Our next egress point is a gateway endpoint. And a gateway endpoint is only used for access to two services outside of your VPC, DynamoDB and S3. The gateway endpoint has a couple of interesting features, one of which is that the traffic that passes across this endpoint is not charged. Another interesting point is that the services you access, the DynamoDB tables and the S3 buckets, must be present in the same region as the VPC where this gateway endpoint is configured. And you can keep your traffic private by using this gateway endpoint because the traffic is passed directly to those service API endpoints without traversing the public AWS network. And by implementing this gateway endpoint, it gives you the ability to further limit access by applying resource level permissions at either the S3 bucket layer or the DynamoDB table layer using their own permissions. This next egress point is similar to the gateway endpoint, but it's slightly more generic. The interface endpoint allows you to access other service APIs, the API gateway, and marketplace products. But this particular endpoint is a charged service. You have to pay both on an hourly basis and for traffic throughput if you'd like to implement one of these. The interface endpoint, like the gateway endpoint, allows you to keep your traffic private by avoiding public AWS networks. And it means you don't have to use any public IP addresses to access the resources on the other end of the endpoint. And it is slightly more flexible than the gateway endpoint in that you can access cross-region resources, cross-account resources, and even resources that are hosted by other customers. Our next egress point is the NAT gateway, and this is one of the few that actually exists inside the VPC rather than attached to the VPC. A NAT gateway is a managed service that is deployed on an availability zone scope that only allows outbound access to the internet. NAT gateways are not associated with security groups. They're only associated with the network access control list that is part of the subnet that they're launched into. And so if you want to restrict traffic through the NAT gateway, you have to implement network access control lists. And by deploying NAT gateways, they become a target for route table entries. And this is how you can help to apply least privilege from your subnets that do not have direct outbound access to the internet. Our final egress point is simply the do-it-yourself version. And this is where a customer decides to deploy a marketplace product or to create their own from scratch that can be used for inline intrusion detection and prevention, data loss prevention, or proxy services, and it's simply launched as an EC2 instance. This gives you full control over the resource. And because you have the ability to deploy marketplace products, you can use commercial versions of existing off-the-shelf products that are simply controlled by the customer rather than by the vendor or by AWS. And with a do-it-yourself solution, you've got the full flexibility to do whatever you like. And by disabling the source destination checking on the network interface, it too becomes a target for route table entries so that you can force your traffic directly through this do-it-yourself endpoint. In this lesson, we've covered edge security. We've talked about what happens when traffic is inside the VPC. We've talked about how to get your traffic outside of your VPC. But what if you've deployed multiple VPCs? What are the security strategies associated with having multiple VPCs in one account or across accounts. And so we're going to talk about some different examples of multiple VPCs in the same region, multiple VPCs in a different region, multiple VPCs in different accounts, and the ability to use a transit gateway to connect your VPCs together. And there are different strategies. It's going to come down to the requirements of the company based on function and security and compliance. But one common way to organize a multiple VPC deployment is by environment. You have VPCs for non-production and production and maybe load testing, and the load test environment gets spun up and shut down as required. And you might have a shared services environment that all of the other environments communicate with. We can organize by workload compliance. Placing all of your publicly facing assets in a single VPC allows you to separate all of the security features from other workloads like internal services or applications that are in scope from a PCI perspective like payment gateways or storage of customer information on databases. The shared services VPC makes a reappearance here because there may be services that are required by all of these other workloads. We can organize by availability requirements. And in this case, maybe we have split up our production environment into multiple VPCs for resilience reasons. Multiple production environments, each in their own VPC, has some advantages in terms of outages and transient failures. You could separate all of your backups and your disaster recovery resources into yet another VPC to provide different degrees of availability as well. If we move away from the single region requirement, we have a lot of options. And if we want to deploy our VPCs into different regions, we might do so by availability requirements. Simply having our production resources deployed into multiple regions is going to increase the overall availability and resilience of our offerings. We can separate our backups, our disaster recovery, business continuity resources into yet another region to improve this further. With different regions, we might want to organize by locality. We could have our deployments for the Americas, for Europe, for Southeast Asia, or Australia located in specific regions that are located in those geographic areas. This allows us to apply different security and compliance rules based on geography. We can also take the concept of multiple VPCs and apply it to different accounts, whether it's in the same region or different regions. And organizing our resources by security requirements, where each of them are in a different account, can make a lot of sense based on our requirements. And organizing our resources by security requirements into different accounts can be a very compelling solution. We could have a single account for security auditors to use that has cross-account access for specific features. We could deploy our backups and our disaster recovery into a single account. Now notice, this is part of multiple solutions. We can separate our non-production and production environments not only into different VPCs, but also into different accounts so that we can apply different least privilege permissions. There's another way of looking at different accounts that's not always based on security. It might be based on company hierarchy. Organizing our accounts similar to the company org chart is another valid way to proceed, where you create different accounts for different business units or departments within the company. Marketing, IT, engineering, or finance. Now finally, there's another way for you to connect your VPCs, whether they are in the same region, same account, different accounts, and this is the offering called the Transit Gateway. When you deploy a transit gateway, you can then create associations with other VPCs, and you can manage the interconnectivity between these VPCs using attachments to the transit gateway itself and route tables. And this gives you even more flexibility on top of the existing offerings like VPC peering connections. There may be a downside, though, to deploying your resources into multiple VPCs. And if you're going to do this, there are going to be some operational considerations. You're going to be dealing with more security groups. You're going to be creating and managing more network access control lists. You're going to be working with more route tables. Now, if you implement something like a transit gateway, this can help to keep it at a manageable level rather than exploding exponentially. It's going to require more routes within those route tables. You're going to be dealing with more egress points, which means more from a security audit perspective, really on all of these different features. And there's going to be overall higher operational overhead. And this means that your organization needs to be mature enough and skilled enough within the AWS ecosystem to take on this operational work. Welcome to our case study for this lesson. And for this one, I wanted to put together a little bit more complicated example of how to design a network, taking into account a lot of the security principles and strategies that we've discussed, and apply that across multiple requirements and multiple scopes. And so our scenario is going to be exactly that. Design a secure infrastructure with multiple networks for hosting and for operations. And so our specific tasks are going to come down to designing an application or network infrastructure for a HIPAA-compliant workload, design a DevOps infrastructure for shared use, and utilize AWS services to eliminate the traffic between the two networks. And so we're going to start with our healthcare application. And we're going to be securing PHI, which is protected health information, through the design of our network. And the first thing we're going to do, we're going to create our subnets according to internet accessibility. And we're going to start with subnets in different availability zones that will have direct inbound and outbound internet access. We will have a second set of subnets that have indirect internet access, which means we're going to allow outbound only. And we're going to have a third group of subnets that have no internet access whatsoever. Now, as we move through our VPC security mechanisms, we're going to be implementing route tables first. And we need to create different route tables for each subnet. And by starting at our top layer, we will apply a route to each of those subnets that will allow outbound traffic to the internet, 0.0.0.0/0, and that traffic will be forwarded through the internet gateway. Our middle tier are going to have outbound traffic routed to NAT gateways that are created in each availability zone. And this is where the different route tables on a per subnet basis are going to come in handy. This is going to be both a resilience design and a cost optimization design, because we're not going to be generating cross-AZ traffic to reach a single NAT gateway. All of the traffic will stay within the same availability zone. And finally, our backend, our protected subnets, will have no route for 0.0.0.0/0 whatsoever. So there will be no possibility of direct or indirect inbound or outbound access from the internet to these subnets. As we move a little further through our network design, we're going to ensure compliance using network access control lists. And as we start at the front end, one strategy we want to deploy is the ability to reject outbound traffic to those VPC or protected subnets on the back end. So it's not physically possible to communicate from the subnets that have direct internet access to our protected subnets. In the middle tier, we're going to reject all non-application traffic, both inbound and outbound. And on the back end, we will only accept inbound traffic to our databases from the application subnets. And so now a little bit about the application infrastructure itself. We're going to be deploying only managed services in the public subnets. So it's not possible for an EC2 instance to be compromised by direct inbound access from the internet. And so for our infrastructure, we'll deploy load balancers in the public tier, and we will associate web application firewall rules with them. Our application infrastructure is also going to be deployed as a managed service with no access to the operating system. We're only going to use temporary resources, and we're going to take advantage of ECS deployed on Fargate within our VPC so that our application will exist only as containers. And on the back end, we're going to place our database in an RDS Aurora engine so that our data is going to be persisted using synchronous replication with a high degree of durability in multiple availability zones within the region. Once we have our resources identified, then we can start to apply security group rules at this resource layer. Our application load balancers will only allow inbound traffic using secure protocols like SSL or TLS, and we will only allow outbound traffic on port 8080 to our applications running in the containers. Our application security groups will only allow inbound traffic on that same listener port 8080 from the Elastic Load Balancer, and we will only allow outbound traffic on port 3306 to the database. The database security group will only allow inbound access on that database port 3306 from our containers, and there will be no outbound traffic allowed whatsoever. So this takes care of our application infrastructure. Let's talk a little bit about the DevOps infrastructure that's going to be required so that we can do continuous integration or continuous deployment. And for this, we've created a VPC that's deployed into multiple availability zones with public and private subnets and an EC2 instance running Jenkins in a private subnet. There are some workloads that we're going to need to configure to allow our DevOps pipeline to work, specifically for access to Jenkins and for Jenkins to have access to our source code directly. For this DevOps pipeline, we need to figure out how the traffic patterns are going to work and how the traffic will be allowed to flow to grant us access to Jenkins itself and to grant the Jenkins server access to our source code. And for this, we're going to force all of the traffic across a VPN, and that VPN is going to be connected directly to our private data center network, where our Git repo is located. And this will allow Jenkins to be able to extract source code straight out of the repo. This same connection can also be used for allowing access to Jenkins via CLI or web browser from our internal company network. So our next question is, how do we perform a deployment if we have no network access to that HIPAA-compliant workload that exists in the other VPC? Well, in order to make this happen, we're going to use our NAT gateway for outbound access to AWS Service API endpoints. And so as this traffic exits the VPC, where is it going? So let's move our VPC out of the way and discuss the Service API endpoints that will need to be accessed for our DevOps pipeline to work. We need access to the ECR Service API endpoint, that's the Elastic Container Repository, and we'll push our deployment artifact, which is just a container image, to ECR using this connectivity. Then we can create our task definitions in ECS and deploy the new service with the updated container. And finally, we can create new listener rules on our application load balancer that allows us to point our traffic to the new service we've created within ECS. And none of this requires network connectivity to our HIPAA-compliant workload. Welcome to our question breakdown for this lesson. And for this scenario-based question, I wanted to apply some of the strategies that we've learned over the course of this lesson, as well as provide an example of a question that has a lot of options and multiple correct answers. Your R&D team is designing a new application, which will consist of multiple tiers as follows. Customer-facing, web front-end accessible by browser on ports 80 and 443. REST API, application front end available to client applications and partners on port 443 only. The application tier, which is where we implement our business logic that only listens on port 8080, and our database tier, which is our relational data listening on port 3306. Both the customer-facing and the REST API tiers need access to the application tier, and only the application tier needs access to the database. Each tier is launched into dedicated subnets. So if you remember back to our case study, this might be a very similar infrastructure. Which combination of security group and NACL rules would be part of a least privilege network security configuration? And we're going to be picking 4 correct answers out of 6 possible options. So let's look at our key terms. It really just applies to our last sentence. Security group and NACL rules, so we're going to be looking for those. And least privilege, that's going to be the highest priority. So let's look at our different options that are going to be a combination of network access control list rules and security group rules, inbound or outbound. And we can walk through these one at a time, starting with A. NACL rule: deny all outbound traffic from customer-facing to database subnets. If you remember from our case study, this is exactly what we did. This is a great practice, and it ensures no direct network access to the database from the web tier. Let's look at B. This is a security group rule. Allow all TCP inbound from the REST API security group to the application security group. Anytime you're allowing traffic inbound on all ports, you should look for ways to restrict that to at least a range, if not a single port. So this is not going to be part of a least privilege implementation. How about C? Another security group rule. Allow inbound access on port 3306 from the application subnets to the database subnets. This is going to be a correct answer because it allows the correct inbound access from our application tier to the database tier. This would be very similar to creating a rule that instead of granting access from subnets, grants access from the application security group. Let's look at D. NACL rule: deny all inbound access from the REST API to the database subnets. This is a good practice. It ensures all database traffic has to flow through the application tier. So now we have 3 out of our 4 correct answers, and we only have 2 choices left. How about E, a security group rule? Remove default outbound rule from all security groups. I can't stress this enough as good guidance. This might increase the complexity of requiring specific outbound rules, but if our primary focus is least privilege, this is also going to be a correct choice. So our final answer, F, isn't going to be right, but let's go ahead and look at it anyway. That's a NACL rule that allows all TCP inbound and outbound to customer-facing subnets. This is the default configuration. This is what NACLs look like when you create them. But if the web tier is only going to allow inbound access on ports 80 and 443, it's a good idea to restrict the NACL to match that, and then your outbound rule would be based on whatever ephemeral ports are required by the connections. And so the correct answers for this question are going to be A, C, D, and E. Lesson 6 covers 2 main topics: troubleshooting network security and the implementation of host-based security. The case study for Lesson 6 is an automated pipeline for managing golden AMIs. In our previous lesson, we talked about edge security and network security. Well, now it's time to take a little bit about what we've learned and apply it to situations where things didn't go as planned. And so I'd like to present a couple of scenarios that I think might provide some likely input to help you study for the troubleshooting questions that you're going to see on the exam itself. For our first scenario, this is going to be based on traffic being rejected between two nodes. And the nodes don't have to be necessarily in the same VPC in the same subnet. In fact, they can be all over the place. They might be in the same VPC, and you could see a question based on that. They might be in different VPCs, same account, different VPCs, different accounts, or either or both of A and B could actually be in a private data center and attempting to communicate through AWS. And so let's look at some possible causes for this first scenario before we dig into an example. First, route table entries. They might not have the correct target. They might be too restrictive. It might come down to an issue with network access control list rules. Maybe an inbound rule was added, but not the corresponding outbound rule. It could be based on security group misconfiguration, inbound or outbound, or even based on a physical data center firewall that is blocking the traffic. And on top of all this, you have host-based security, which we're going to talk about a little bit later, where a host-based firewall could actually break that connectivity, even though everything else is fully configured. You can also run into problems where your do-it-yourself firewall, whether it is deployed through the marketplace or completely do-it-yourself as an EC2 instance, becomes the problem. And so let's look at some diagrams. If we wanted to isolate a route table entry as a possible cause, remember, route tables are associated with subnets, not with instances or nodes on the network specifically. And so a route table misconfiguration in a scenario where you have two VPCs that are paired together could actually exist on either side. It could be a route table in the first VPC that is configured incorrectly or not configured at all. It could be a route table in the second VPC that is likewise misconfigured or completely missing entries. Our next example would be based on network access control lists. And remember, because these are stateless firewalls, you do have to create rules in both directions if you are attempting to use them for whitelisting. And because NACLs are also associated with subnets, you're not going to be looking at the individual nodes themselves except to determine which subnets they are part of. And then you can review the network access control list inbound and outbound entries to determine if there is a problem. Because we're working with stateless firewalls, it can be inbound rule that's missing or misconfigured, an outbound rule that's missing or misconfigured, and it can actually be the same thing on the destination. Inbound or outbound rules missing or misconfigured. This makes for a lot of complexity and becomes a good reason for utilizing security groups where possible for whitelisting your traffic. Security group configuration then comes down to how that application traffic flows. If you were to have a missing or misconfigured outbound security group rule in that application security group where you have EC2 instances that are part of an auto-scaling group, they might not be able to communicate with B, which is your database. You could run into a problem where your database, maybe being deployed in RDS, has a missing or misconfigured inbound security group rule. Now remember, there are certain rules that will not apply to this scenario. The security group that applies to A, the inbound rule set does not matter. The security group that applies to B, the outbound rule set does not matter. Now, if we take this to a hybrid deployment where we have an on-premise network and an AWS infrastructure, we look at A and B, where A is in AWS, B is sitting in our corporate data center. We could run into a problem where our corporate firewall is actually rejecting the traffic from A very close to the destination. You could run into a scenario where the traffic makes it all the way to the destination B and is then blocked by the host-based firewall. You could run into a scenario where you have an inline firewall that you've implemented inside of your VPC that acts as a proxy or a router that is rejecting the traffic for some reason. And any of these can end up being a root cause that would enable you to answer the question that is based on troubleshooting. Let's cover a second scenario. For this one, it is based on a user who is unable to modify a network resource. And this is kind of a loaded term for the word modify. It could be that they made the change and then the change is not visible, or it could be that they were not able to make the change in the first place. And so there are different types of example network resources that the user might be trying to modify, like a route table, security groups, network access control lists, or virtual private gateway, or even other VPC resources, but they're attempting to use the Service API endpoints in some manner to make this change, whether it is CLI, SDK, or AWS console. Possible causes for this one are going to be pretty clear. It could be a situation where an IAM policy is not permissive enough to allow the user to perform the work. It could be based on account permissions, where possibly the account is part of an AWS organization and the SCP that's applied to that account does not allow that work to be performed. Or it could be based on other API issues. And one interesting possibility here is that the AWS Service API endpoints have a security feature that is enabled to help them avoid man-in-the-middle attacks or replay attacks. And what it means is that if your request reaches the Service API endpoint more than 5 minutes off of true time, then the request is simply dropped on the floor because AWS is going to assume that it is from an improper source. So a root cause of being unable to modify a network resource could be that your local time has drifted by more than 5 minutes. So let's look at a couple possible causes for a change not being able to be made. Let's start with a change where the user is trying to make a change to the VPC itself. That change is going to be sent to the VPC Service API endpoint, the generic one that is region scoped, and this would be the generic Service API endpoint that is hosted by AWS in the region. So there are different ways for an account to capture this change. One of them might be an AWS config rule. Another might be a CloudWatch events rule where the change that is being made matches that rule. It could even be captured by a feature called CloudFormation drift detection. And this is where the VPC has been deployed as part of a CloudFormation template. And when an attempt is made to change the resulting stack, that results in a drift and is marked by CloudFormation. Any of the three of these could be used to trigger a Lambda function with code that could revert the change. And thus, the user would see that their change went through, but when they go to look at the resource or query it, the change has been reverted. We've covered a lot of the elements of network and edge security. We've talked a little bit about troubleshooting, but one area that we've neglected is the security that you apply at the host level itself. And so we're going to cover some of the different strategies that can be used to help implement host-based security in AWS. If you referred back to the shared responsibility model for security, the customer is entirely responsible for everything that happens within the operating system of an EC2 instance. This includes everything from user accounts to OS patches, to OS updates, to hardening the operating system in various ways. And so in order to maximize your chances of having a secure OS, it's a good idea to start with an AMI from a trusted source in the first place. A source that you trust would either be an internal source or an external source from a vendor or other provider where you have a degree of trust in the image that they are deploying and making available for your use. The next thing you can do is to launch that resource into a VPC or a network that you have secured using all the strategies that we have discussed up to this point. But you're not done. After this point, it is time to implement additional security on the operating system. And this can happen in a number of different ways. It might be by implementing or configuring the OS firewall. It could be disabling services that are no longer needed. Taking it a step further, remove packages that are no longer in use or will not be in use by the application. You can implement monitoring from the AWS perspective, installing the CloudWatch agent or the CloudWatch Logs agent. All of these can be helpful to making the OS a little bit more secure, or at least to give you a notification if it becomes insecure. But AWS monitoring might not be the entire solution. You can install third-party monitoring. There are a lot of options out there for monitoring EC2 instances that are perfectly valid, and if your company has already standardized on one of them, by all means continue to use it. You should be restricting user access. This is actually a bigger topic than what we have the scope for right now because it involves more than just deploying only a small number of user accounts. It can also mean restricting the necessity of logging into the operating system in the first place by making sure that you have automated mechanisms for performing work on that instance that don't rely on an interactive login session. You could even take that concept a step further by deploying an immutable operating system, one where changes are not allowed to be made at all. An auto-scaling group is a great example of an immutable OS. One way of being able to perform regular audits to ensure whether or not the operating system remains secure is by using a service called Amazon Inspector. Amazon Inspector does require an agent to be installed on the instance. You can do this by hand. You can do this as part of the AMI. You could do it according to whatever automation is appropriate. In order for Inspector to be fully functional, you'll have to create an SNS topic to send the findings as notifications. From there, you configure your assessment template. This is where you choose which rules are going to be applied to the instance every time you execute one of these assessments. Then, schedule an assessment run. This can be based on a particular start time, but it might also be based on a time window where the job runs for a certain period of time and then must stop at the end of the window, whether it has completed the work or not. And then execute the assessment. And this is where findings are generated, and you have an opportunity to start to think about ways of automating mitigation. One example of how to automatically mitigate or remediate findings is to implement the built-in feature where you post the finding to SNS. You set up a subscription with a Lambda function to that SNS topic that will parse the text of the finding. After parsing the finding, the Lambda function could then potentially invoke SSM run command. This is a service that allows you to interact with the operating system without requiring explicit keys or specific network access from the client side. And the SSM run command could be in the form of installing a patch that remediates the finding and could even then trigger another assessment to make sure that the finding has been properly mitigated. Now, I wanted to talk about a couple of options around the immutable operating system. The idea that once you deploy these OS images, you don't change them after the fact. This is a great way to improve the overall security of your infrastructure, as well as the reliability of expected performance, because you're not making manual changes. One way to do this is to deploy your compute resources using an auto-scaling group with an AMI. In order to update the operating system or make any other changes, you would need to change the AMI that is associated with the launch config, and then deploy changes in the form of replaced EC2 instances across the fleet to propagate the change. Another way to go with immutable OS would be to use Elastic Beanstalk. This is a fully managed service where you still have access to the EC2 instances. But Beanstalk gives you a choice. You can choose to deploy changes to your Beanstalk app where it replaces the instances, but it's not a hard requirement. And because it's optional, you'll want to make sure you understand the ramifications of your choices. Now, if we want to remove the operating system from the equation entirely, we could work with a service like ECS, the Elastic Container Service. This service provides the capability to deploy Docker containers or Windows containers on a back-end compute service that is entirely serverless called Fargate. And in the case of Fargate, you have no access to the OS whatsoever. No SSH, no access to the operating system, nothing. Another way to go entirely serverless is to simply use Lambda functions. If you can deploy your business logic in the form of the custom code as Lambda functions, you don't get the access to the operating system. You also don't get the access to the container itself. And this is a way of reducing operational overhead in addition to potentially increasing the overall security of your application infrastructure. Welcome to our case study for this lesson. And for this one, I wanted to choose a scenario that required a number of different workloads to be implemented in the form of operations and details to make sure that you're working towards host-based security in an automated fashion, while having taken advantage of all of the network security that we've already discussed, including possibly having multiple VPCs and multiple accounts in multiple regions. And so our scenario is going to be designing an automation pipeline for the creation of a golden AMI. The golden AMI is going to be the image that you have approved for use across your organization for most use cases. And so we have three things to accomplish. We need to set up the pipeline infrastructure. We need to share the approved AMIs with the rest of the organization. And then we need to discuss possibilities for deploying those updated AMIs into existing stacks. For step one, the golden AMI pipeline infrastructure is going to start with either a base AMI or an AMI from another vendor that you trust that you know you're going to need to make further changes to. So the first piece, launch an EC2 instance from this base AMI. Next, that user data script at launch can perform some kind of basic validation. Maybe you're looking at checksums for particular executables or permissions on specific directories, or even making sure that certain packages are there. There's a lot of things that can be done in a user data script, and really the flexibility is there that you can do whatever is necessary to get that basic validation out of the way by the time the instance is in a running state. From that point, you can execute patch installs and library updates via SSM run command. By tagging the instance appropriately to begin with, these patch installs and library updates can be run as part of a scheduled job, or they could be triggered through CloudWatch events or a Lambda function. This task also includes all of the operating system hardening strategies that we talked about in the previous section. Everything from OS updates to disabling services, removing features that are no longer needed. But all of this is done via SSM run command. So up to this point, nobody has logged into the EC2 instance using an interactive session. At this point, it's appropriate to stop the instance, assuming all of the SSM run command jobs completed successfully. Once the instance is stopped and you have proof that the EBS volumes have been fully quiesced, you can create a new AMI from this instance. This will be your golden AMI candidate going forward. The act of creating that AMI of the instance could kick off automation, which then tags the AMI, including the current date, patch levels, output from SSM run command, and so forth via CloudWatch events. And once the AMI tags are in place, that can trigger other activities using CloudWatch events and Lambda, which would then launch a new instance from the newly created AMI into your infrastructure. From that point, you can install the inspector agent and perform a full assessment of the operating system security using SSM run command, or even a scheduled assessment in Inspector itself. All of the findings are then posted to a predefined SNS topic and sent to an approver. And at this point, we can consider this a human toll gate as to whether or not the new golden AMI is going to be approved or rejected. Assuming that this human toll gate then approves the AMI, then it gets automatically tagged using a Lambda function as ready to distribute. And this will take care of the first of our 3 tasks. As we move on to task 2, now we have the job of sharing this AMI across the organization. And for this to happen, when that new golden AMI is fully tagged and approved, that's going to generate a CloudWatch event, which can be used to trigger a Lambda function that will share that AMI with all of the other 12-digit account IDs within the organization. Because CloudWatch events can have multiple targets, you can also use this to forward the event to all of the other account event buses. So we've shared the AMI, and we've forwarded the event to all of the other accounts so that they are aware that a new AMI has been created. And that completes the second step out of our 3 tasks. So let's move on to the last and final step, and this would be to deploy the updated golden AMI into existing infrastructure. So if we take the view of one of the other accounts in the organization, they're going to view the inbound event stating that there's a new golden AMI captured by CloudWatch events. That CloudWatch event can be captured by a rule and sent to a Lambda function as a target that would then deploy updates according to infrastructure using the SDK or even the CLI using SSM run command. And there are some different options that we have from this point forward depending on our infrastructure choices. If we assume that we have deployed auto-scaling groups as a CloudFormation stack, all the Lambda function would need to do is update one of the parameters for the stack that specifies the AMI, and then perform a stack update. And then CloudFormation will automatically deploy rolling updates to replace the EC2 fleet that is part of that auto-scaling service. If you have infrastructure that is deployed via Elastic Beanstalk, there is a very slick way to deploy these updates with little to no impact on the end users. And one way to do this is to clone the existing Elastic Beanstalk app using the new EMI. And that's going to create a brand new application infrastructure running the same version of the application, but the updated OS image. Assuming that you're using DNS to point to the existing application, you would then make changes to the Route 53 zone entry that points to the old version of the Beanstalk app, point that to the new one instead, And you can treat this as a blue-green deployment where you could even gradually migrate traffic from the old version of the app to the new version of the app using weighted round-robin records or some other mechanism with health checks. And when you are ready, you simply delete the old Beanstalk application. For this question breakdown, I wanted to cover another troubleshooting scenario. And so let's just dig right in. A company has recently completed a number of improvements to their network security. Some of the modifications included removing the internet gateway and implementing gateway VPC endpoints for S3 access from inside the VPC. An application that was previously functional is now unable to access S3. Which of the following troubleshooting steps would not identify the root cause? Now, before we go into key terms, just want you to keep in mind, we're looking for an exception here. We're looking for an answer choice that would not be a troubleshooting step in this particular infrastructure. So our key terms are going to be the fact that we no longer have an internet gateway, so we have no choice but to go through the gateway VPC endpoint to hit S3. And the application that used to work is now broken. And let's walk through these answer choices one at a time. We'll start with A. Analyze the network ACL rules associated with the application subnets. Now remember, we're looking for something that would not be a good troubleshooting step. This actually would. The NACL rules have to be permissive in both directions for the traffic to flow. And if part of our network security improvement was to make changes to the NACLs, that could absolutely have broken the application access. So let's look at B. Analyze the route table associated with the application subnets. Well, in order to be able to use a VPC endpoint, it requires a route table entry. This is another valid troubleshooting step, and therefore not the answer. How about C? Analyze the bucket policy that is associated with the S3 bucket. Guess what? This is another excellent troubleshooting step because that bucket policy must allow access from that VPC gateway endpoint, either explicitly or at least by not having a deny. So this is a reasonable step, not the correct answer. D, analyze the application security group inbound rules. Now with this one, if we go back to all of our network security and we think about the one-way flow of data, security groups are stateful firewalls. And therefore, you only need to allow access in one direction. Well, the security group inbound rules has nothing to do with the application being able to initiate outbound connections to S3 through that gateway VPC endpoint. And this would be a correct answer. So let's look at the final choice. Analyze the application security group outbound rules. This is also a reasonable troubleshooting step because there either needs to be the default outbound rule that allows all traffic or a more specific outbound rule that would then allow that traffic to be initiated from the application directly to that gateway VPC endpoint. And so our correct answer to this question is D. Welcome to Module 5. In this module, we have 2 lessons to cover the 4th exam question domain called Identity and Access Management. Lesson 7 will detail the mechanisms for permissions and roles. In Lesson 8, we'll discuss federation and resource-based access control. In Lesson 7, we will discuss the details of IAM policy elements focusing on conditions. After that, the lesson details policy evaluation logic and the process of assuming IAM roles. The case study for this lesson will cover several IAM policy examples. Welcome to the first of the two question domains, where I recommend that you spend the majority of your study effort. For this particular lesson, though, we're going to focus on the first half of the question domain, which involves designing and implementing a scalable authorization and authentication system to access AWS resources, and then troubleshooting the same. But before we dig into that, we need to cover a couple of terms and keywords so that we can make sure we're discussing everything with the proper foundation. Now, the first word is authentication. And in an AWS context, there are some very specific words that you can look for on the exam that will lead you to this particular question domain. Authentication is just proving that you are who you say you are using some predefined method of proof. And within an AWS context, this can mean a username and password. For example, if you're logging into the AWS console. It can mean any number of API keys that you can use. It can even be an MFA device, which stands for multi-factor authentication, such as a hardware or software token that has a rotating number that you would type in addition to some other authentication. It is also possible through federation, where you're actually authenticating to some other identity provider and then using that authentication to gain access to the AWS ecosystem. The second term we're going to talk about is authorization. This is where you get permissions to perform actions within AWS. And there are a couple of different ways that this will show up, especially on the exam. It can be based on user access control. It can be resource-based access control. But one thing you want to keep in mind, and this is really important for certification, is that by default, you are denied all actions. If you create a resource or a user, by default, they have the ability to do absolutely nothing. And that's going to be important when it comes to the order of operations of evaluating the different types of permissions that are possible within AWS. The next thing I want to talk about is the fact that everything in AWS is 100% API driven. This is based on a memo that was sent out by Jeff Bezos over a decade ago, where he specified that from that point forward, all of their engineering efforts and all of the services and offerings that they created, whether they were made available to customers or only used internally, would be exposed to each other using API interfaces only. No more backdoors, no more tricks, no more special access between two services for groups that know each other well. Everything is exposed directly using these APIs. And this is going to be important because it's going to help you understand the communication you're going to be generating with AWS and the way that the services are going to be talking to each other. Now, within AWS, there are a couple of different ways for you to access the service API endpoints and provide authentication. The first of these is just going directly to the API endpoint itself using HTTP or HTTPS. And for this mechanism, you have to provide API keys, but the signature is manual. You're going to have to generate this signature via code, which might be a little bit of extra work. You can use the command line interface. And with the CLI, it also uses API keys, but your requests are automatically signed as part of the CLI libraries. Similarly, if you use the software development kits or SDKs, you're going to be using the API keys, and your requests are automatically signed. And really, the differences between the CLI and the SDK are a matter of preference on the part of the customer. And the final mechanism that you can use as far as direct access to the service API endpoints is the AWS console. And this is a little bit different. This is going to require that username and password authentication rather than API keys. And these requests are also automatically signed. So these final three mechanisms are all going to be pretty efficient from a customer perspective. CLI, SDK, AWS console, none of these are going to require that manual signature. What are the benefits of signing your requests to the AWS ecosystem? Well, first, That means that you have proven you are who you say you are. Not only are you providing the username and password or the API keys, but by signing the request, that is going to be the final proof of your identity. This helps to avoid tampering. That signature is going to be unique to you and your request. And so this is going to help avoid things like man-in-the-middle attacks. Now finally, this is going to help avoid replays. If someone is watching your network connection and creating a dump of it using Wireshark or TCP dump with the intent of modifying and possibly replaying it later, they're not going to be able to do that because that signature is the part of the request that must show up within 5 minutes of true time. There are also indirect ways of accessing the service API endpoints, and there's a couple of different ways you can go about this. One of them is by allowing services to communicate with each other. We can call these just cross-service API calls. And for the majority of these requests, they are simply going to be assuming an IAM role from one service to another using STS, which stands for Security Token Service. Another way for indirect access is by using SAML federation. And we're going to be talking about this quite a bit later when we get into federation. And this also requires you to assume an IAM role via STS. But the authentication for this is happening on the SAML provider side and not explicitly on AWS. There are other ways through certain services where you can actually use an email address to authenticate. And one of these is QuickSight. QuickSight requires an email address in order to be able to authenticate. Cognito gives you an option of using an email address for authentication, but it's not required. We're going to talk about Cognito quite a bit when we get into federation. Other services use an actual service, AWS Directory Service, for their authentication. And for the most part, these are going to be the enterprise level services that kind of sit farther up the stack than most of the rest of the AWS offerings, like Workspaces, WorkDocs, and WorkMail. But also, the AWS Single Sign-On service gives you the option of using the AWS Directory Service if you don't already have another identity provider for authentication. It's time to dig into IAM policies, and we're going to be dissecting IAM policies down to the individual elements because as part of the certification, you're going to be expected to understand these at a pretty deep level. IAM policies are made up of a number of different sections that have varying degrees of importance as far as the exam is concerned, but you're going to be expected to understand all of them. And in fact, from the certification perspective, there are certain areas where you're going to want to spend more of your time because they are the more complicated sections of an IAM policy. And so let's get started. We're going to go through these one at a time, and we're going to discuss what their uses are and how not to use them in some cases. And we're going to start with the version section. And this is pretty simple. It's just a date, and it can be the policy language version. It should be a static number, and there is actually a default. There is the 2012-1017 version number. If for some reason you try to use the previous version, the 2008-1017, there are features that are not going to work. What this does is that it instructs the IAM service to interpret your IAM policy as if it were based on the older policies. And so there really isn't a good business case for ever using the previous version, but you do want to keep track if AWS does decide to release an updated version beyond the one from 2012. ID is next, and this is going to be an element that is actually optional. It's just an identifier for the policy, and it's arbitrary text that you can apply. There are going to be some services that will require an ID, but they're going to be very explicit in their documentation that this is going to be a necessary element of your policy. Now, there are some recommended values that you can use here, like the UUID, that are part of the AWS ecosystem, where this might be a good place to put it. The next section is going to actually be comprising the rest of the policy, and this is going to be the statement section. This is the main policy element. This is the big one. This is where everything else resides. And as far as the exam is concerned, everything that is inside the statement section is going to be where you want to spend your time studying. All the logic is going to go here. The conditions, the actions, the resources, all of that is going to be inside of this section. Now, once you get inside the statement, you can have a second optional identifier called the SID. And so you can identify the statement where you can describe what it actually does. This is great if you have large teams of people who are working with IAM, and maybe your processes aren't quite automated yet, and so people are going to be reading through these by hand, trying to figure out what they do. Giving them a clue through the SID is a good way to go. There are a couple of services, much like the ID, that do require this, but they are very explicit in their documentation as well. These are not directly exposed in the IAM API, and what that means is that when you get to conditions, you're not necessarily going to be able to look at values in the SID to determine whether or not the user or other entity is going to be able to be granted access to a resource. Now, as we get into the next several sections, this is where you're going to start to get into actions. This is where the rubber meets the road. And let's start with effect. Now, effect is going to determine whether or not the policy is going to result in either an explicit allow, which means you might be able to do it, or an explicit deny, which guarantees you won't be able to do it. And both allow and deny are going to be in scope from an exam perspective. Explicit denies are really important in terms of making sure you get least privilege implementation. This is also a required element. You will not be able to create an IAM policy without having the effect section. The only valid values are going to be allow and deny. Principal is where things start to get interesting. This is where, rather than having a number of set values, you start to have some flexibility on the types of values that you can work with. Now, the principal is going to describe the entity that is either going to be allowed or denied access to the resource or resources that are described in the statement. And a principal can be represented by one or more specific AWS accounts using the 12-digit account ID. It can be one or more IAM users where you're specifying the Amazon resource name for the users. It can be federated users based on web identities. So a web identity might be a Google account or an Amazon.com account or a Facebook account. Any of these can represent a federated user. A principal can be a federated user from a SAML provider. All of these are in scope from a principal perspective. And so you'll want to keep in mind when we talk about principals and then when we dig into resource-based access controls. For the services that have access control policies, principals in those services can be described as they are here. Now, as we dig a little bit further, principals can also be an IAM role. So assuming that an end user has assumed a role or a service has assumed a role, they might then be granted access based on the fact that they have assumed that role. It can be a specific assumed role user. So this is going to be more specific than just an IAM role. It can be an AWS service. This is partially how IAM roles are created in terms of the trust policy. It's going to specify which service is allowed to assume the role. And finally, your principal can be everyone. And for this, you would just use an asterisk. Be very careful about doing this. This means that you are granting access to everyone if your action is also allow. Our next section goes along with principal, but it's not principal. There are a number of sections that also allow nots, and it is very important for you to learn how the nots work, where they're appropriate, and where they shouldn't be used. A not principal is really just the same concept as a principal, where you supply the same types of entities, but it's used for exceptions. When you want to grant or deny access to everything but a particular principal. This is a great way of defining using a smaller IAM policy rather than having a gigantic list of principals that should or should not be allowed to do something. Now, with a not principal, you do want to avoid using it with allow statements. And the reason for this is if you create a statement that has not principal and allow, you are essentially granting almost anonymous access except for one particular resource. And that can have unintended consequences if everyone except for one principal can access a resource. This is much better to be used with deny statements so that you can implement least privilege policies with a shorter policy document. Next, we want to move on to actions. And this is where it really starts to become flexible. Actions are going to be specific tasks, actions that can be allowed or denied. And there's a huge selection as far as what you can place inside of actions. Each service is going to have its own actions, and you can think of these as roughly equivalent to a REST API method. And so even just thinking about the API service for EC2, there are probably 150, 200 different actions just within EC2 that can be performed. You can also combine actions from multiple services within the same statement if you turn this into an array. So what types of options are available here? You can create an action that is just everything in AWS. So more specifically, what are your options? You can specify everything in AWS. You could specify everything that's within a single service, like EC2. You could name actions within a single service. So think of these as REST API methods, like EC2:run instances. You could provide an array that is named actions in multiple services if you want to combine services in a single statement. And AWS makes it a little bit easier for you here by giving you the ability to use wildcards with an asterisk. Now, you guessed it, there's also not actions. Not actions are going to be the same concept as an action, but you're going to be using these for exceptions, similar to the not principal. Much like the not principal, this is easier than defining a long list. Now, with not actions, you can use these with allow statements so that you can allow everything except a specific action. You can also use these with deny statements to create shorter least privilege policies, but both of them are reasonable use cases, unlike the not principal part of the statement. Let's move on to resource. And this is going to be the description of the object or objects that are going to be in scope for the statement. Resources are always specified using their Amazon resource name. That's the full-length string that includes the 12-digit account ID and the service, and then the resource-specific identifier. But just recognize not all services support resources being anything other than an asterisk. We also have the ability to use a not resource. It is the same concept as the resource, but as you guessed, it is going to be used for exceptions. And much like the other nots, it's easier than defining a long list. And in a lot of ways, it's a way of making a simpler policy. Not resources you want to be very, very careful with, because if you are using this with either allow or deny statements, you could grant or deny access in an unintentional manner. You could either deny access to almost everything, Or you could grant access to almost everything without realizing what you've done. And so you want to be really careful with not resources and the other nots, that you're testing your statement using the policy simulator that you can access through the AWS console. The final section of the AWS IAM policies are conditions, and this is where they really start to get complicated. This is a section that you really want to make sure you understand backwards and forwards for the certification. You will see questions on the exam where you are shown an IAM policy and you're expected to be able to interpret it, including conditions. And this does exactly what it sounds like. It specifies conditions for when a policy will be in effect and when it will be evaluated. There are a couple of gotchas here, like case sensitivity, and so you want to be very careful about the key names that you use in your conditions. And that some conditions only apply to specific services and not to others. This is a great place for you to do a combination of hands-on testing and reading the documentation. So let's start with the first and the easiest. It's the string condition. And this is where you're going to be testing a string that is part of the request or the condition or environment surrounding the request. You can specify an exact match. You could specify a partial match, and you can use wildcards for this. You can even do a negated match, so everything except a particular string. You can specify numeric conditions, and much like string conditions, you can do exact matches of particular numbers. You can do a negated match of a particular number, or you can do inequalities, greater than, less than, and so forth. Date conditions, these are pretty straightforward. You can specify an exact date and time, which really doesn't have a lot of utility because you have to be so specific that it would be really difficult to actually meet the condition. But you can also do everything except particular dates and times, which might be a little bit more useful. You can specify that it be before a specific date or after a specific date, and you can have multiple date conditions within the same statement. So you could specify a time range. Next would be Boolean conditions. And this is where you're doing a Boolean evaluation as true or false as to whether or not something exists or you've met another condition. This is another way to evaluate strings, for example. This is also a way to force the usage of SSL for accessing the service. Our next condition is a binary condition, and this is where we start to get into the corner cases. A binary condition is where you're going to test a key value in binary format. It's going to compare the value that you've provided in the condition to the base 64 encoded binary value in the policy. IP address conditions. This is going to be one of the more popular uses of conditions, where you're going to specify either an IPv4 or IPv6 range that has to be tested from the requester side to make sure that they meet the condition. It does require knowledge of CIDR format, so you will have to specify it in that format. You can't just specify a single IP address. You would have to specify the IP address /32, for example. You can create ARN conditions. And this is where you're going to do a case-sensitive match of any or all elements within an ARN, but you can also do a negated match. So you could match everything except a specific ARN. This is one of the conditions that isn't supported by all services. And so again, you'd want to dig into the documentation to make sure you understand which. And as we start to get to the end, we reach if exists. And this is a postfix that you can apply to other conditions so that you can specify if the key exists as part of the other check. And this one has some pretty cool use cases. Now, when we get into our case study here in just a little bit, we're going to go through a number of examples of different types of conditions and policies and how to interpret them. The final condition is a null check. And this is going to be used alongside the if exists condition, where all you want to do is to check if the key exists as a standalone check. One of the most important concepts that you should have cemented into your brain is how policies get evaluated when you attempt to perform an action in AWS. We start with a principal, and the principal would like to perform some arbitrary action against a Service API endpoint. The default answer is no. That default implicit deny is going to be at the back of your mind for the rest of this conversation, recognizing that if all else fails, you can't do the action. So let's start in on the policy evaluation logic. First thing it's going to do is it's going to look at all associated policies against the resource. Identity-based policies, resource-based policies, ACLs. And it's going to extract all of these policies for evaluation. Next thing it's going to do is going to look for an explicit deny in any of these policies. Now, ACLs don't have explicit denies, but identity and resource-based policies can. If there is an explicit deny anywhere in these policies, you're done. You're finished. There's no way for you to perform the action because that explicit deny is going to take precedence over everything else. Let's keep moving though. Let's assume that there is no explicit deny. Next thing it's going to look at is whether or not your AWS account is part of an organization and is there a service control policy. If there is, it's going to look for an explicit allow within the SCP. If there is no explicit allow in an existing service control policy, you're done. You cannot perform the action. But assuming this is not the case, then it's going to go back and look at all of the applicable policies again. And it's going to look for permission boundaries. This is going to be primarily for the IAM-based resources. And a permission boundary is going to be the definition of what is possible within the policy document. So we're going to look at all of the policies, especially the IAM policies, to determine whether or not there are permission boundaries assigned to the user object. Permission boundaries are going to determine the maximum possible permissions that can be defined within the policy documents themselves, and it's going to look and see if they have an explicit allow as part of the permission boundaries if they exist. And so if the permission boundary exists, and there is no explicit allow, you're done. You cannot perform the action. Assuming that's not the case, we move forward, and it's going to look at the resource-based policies now. And if the principal, assuming this isn't the case, we move forward. And now we're going to check and see if the principal is assuming an IAM role using STS. And if it is, does that role have an explicit allow? And again, if we have an IAM role being assumed and no explicit allow, we're done. Assuming this is not the case, now we move on and we evaluate the resource-based policies. And if a resource-based policy exists, and if it does have an explicit allow, at this point, you will be able to perform the action. Note, if your IAM-related policies do not have an explicit allow anywhere in them, but the resource-based policy does, then you can perform the action. And this is an important distinction to make over a lot of the other descriptions that you're going to find online. It is still possible to perform actions in AWS even if you don't have explicit IAM policies granting you access to do so. Now we move on. Assuming that you're still not granted explicit access to perform the action, now we're going to go back and look at all the policies again, but mostly from an IAM perspective, and we're going to determine if there is an explicit allow in the IAM policies associated with the principal. And if this is true, this is the only other condition under which you can perform the action. If there is no explicit allow, then you're done. The concept of an IAM role is analogous to other terms that are used across system administration. If you've ever used the sudo command on Linux to change your user privileges to root or some other user, that's similar to an IAM role. On Windows, if you've ever right-clicked on an executable or a document and specified Run As, where you choose another user, that's similar to an IAM role. The idea behind an IAM role is that you are going to replace your current privileges with some other permission document. And an IAM role using the security token service is one way to achieve this. And so in our scenario here, we have a user who needs to create a new IAM user account within AWS. And so they attempt to perform this, whether it's through the console or the CLI, and they realize they don't have permissions to perform this particular action. And so the way that we might grant that would be to create an IAM role that the user is going to be allowed to assume. And an IAM role has two elements associated with it: the trust policy and the permissions policy. The trust policy requires a trust relationship that can be with a principal, such as an IAM account or an actual service within AWS. In this case, the trust relationship would be with the same account in which the role is created, the 12-digit account ID formed into an ARN. The permissions or access policy is going to grant permissions for the user to be able to perform the IAM create user action. And so we would then modify the existing user permissions to allow them to perform the STS assume role action. And the user would specify the ARN of the role that we just created. Once they have done that, the user no longer has their former permissions. They only have the permissions that are associated with the IAM role that we created. And so now they can perform the IAM create user action. But if the same user would like to be able to go back and do their regular job, they would actually have to exit the role and go back to their regular permissions. IAM roles can be used for cross-account activities as well, and this is really important if you want to follow a lot of the best guidance for having multiple accounts within an organization. When you create IAM roles that use the 12-digit account ID of another account, you're also going to want to provide an external ID. It is optional, but strongly recommended, and it's just an alphanumeric string that must be supplied during the assumption of the role as sort of an extra authentication feature. This is going to help prevent unauthorized access through the trusted account. Now, when you create that trust relationship as part of the IAM role, that relationship is with the entire 12-digit account ID that you've specified. It's not going to be for a specific IAM resource. And so you're going to trust that remote account to own the further restriction of privileges. And this is where that external ID comes in handy. Let's say that the account that has been trusted to assume a role also has remote users where it is trusting remote accounts. And you don't want any kind of unintentional access where a user that is removed from your account by 2 levels assumes a role in the remote account and then assumes a role in your account. That's where the external ID is important. When services communicate with each other, much of the time they're going to use IAM roles also. And there's a concept of service-linked IAM roles that are going to be unique to each service. This is what allows services to call each other using predefined methods. And each service is going to have the option of a service-linked IAM role. And you're going to want to dig into the documentation to find out which ones use them and how they're created. Because the service-linked IAM roles are not necessarily an automatic thing. Sometimes they're created during the first time that you use that cross-service integration, and there's no action on the part of the customer except to create that integration. Sometimes they're created as part of a wizard, where you're asked if you'd like to create the role and provide the permissions. Sometimes the wizard will ask you if you've already created a role that you'd like to use instead. Others require you to create this service-linked IAM role manually or programmatically. And there are certain services where the only way to create this role is by using the command line interface. This is where having the hands-on experience is a lot better than simply reading documentation, because you might miss a small detail like a service-linked IAM role requiring a command to be entered before you can actually use the service. The permissions policies that are created as part of these IAM roles cannot be used by any other entity. They are only for the integration between that service and other services. Welcome to the case study for this lesson. And rather than having a single scenario that walks us through a number of permissions, I decided that it would be more valuable to provide several different examples of policy documents that you might see on the exam, and then explain how to interpret each of these, as well as providing an example of what they might be used for in a real-world situation. So our scenario is going to be explain the permissions defined by a given policy. So let's start with example 1. This one looks pretty simple, pretty straightforward. And you can see that we're going to be working in the S3 service, all buckets, and with a condition. So let's walk through these. These first 3 lines, effect, allow, action, S3:* and resource*, that means you're allowed all S3 actions with no restrictions. The next section is we're going to be applying a condition that's going to be based on the date. And as long as the date is greater than a certain time and less than another certain time, this is going to give us a date range. And if you look at the actual dates, you can see that it would be 2019, March 11th to March 15th, between the 11th at midnight and the 15th at 11:59 p.m. This could be used for a lot of different reasons, including an example of a one-time cleanup job where an existing account is going to be used to perform quite a number of actions that might be outside the scope of their normal operations. So let's move on to example 2. Example 2 is going to be a little bit more complicated. You can see that we're going to be working with IAM now instead of S3. We have a statement with multiple effects within the IAM service. If we start at the top with the first effect, we're going to be allowing the action of IAM get account password policy for all resources. This allows the retrieval of that account password policy. But why? Why do we want to do that? That's where the second effect comes into play. For this, we're going to be allowing IAM get user and IAM change password. This allows the principal to describe user metadata and effect a password change in addition to the previous permissions of determining the password policy. If we granted a user this particular statement without any resources applied, or by using resource of star, that would give the user the ability to change the IAM user password for every account, every IAM user within that AWS account. That's not least privilege. And so we take advantage of some built-in features of these IAM policies and their evaluation by specifying a resource using an ARN that has a variable in it. If you look at that ARN, it is AWS IAM star and then user /, and you've got this $AWS username. That will only allow the user to change their own password and to get their own user metadata. And so this would help us implement least privilege. And so with this, users can view their own information and perform the password changes as self-service without impacting any other user account. Our third example is going to be stretched into multiple parts. The first part of this is going to be going back and working with S3. And you might think of this as a policy that you might apply for cross-account actions, or even for a very specific purpose within S3 for an application. We're going to start with the ability to list S3 buckets. But we're going to apply the condition that it's only going to be possible to list buckets when the string is based on the name of the bucket. We're going to use S3 bucket name as our example bucket. And so with this first effect, we will only be able to list the buckets, and it will return this one bucket. The second part is where we allow actions within the bucket. And you can see we have a number of actions here. List bucket, put object, get object version, delete object, and delete object version. So this is going to provide most read and write privileges upon the bucket and its objects. But how do we make sure that it really is only this bucket and the objects within the bucket? That's where we restrict according to the resource. And you can see that there are two ARNs listed. The first one is the bucket itself. The second is going to match every object in the bucket. Both of these are required to be able to perform the operations. So this example might be attached to an IAM role that would be granted to a partner with access to a specific bucket. Notice they don't get the ability to delete the bucket itself. They don't get the ability to work with management of the bucket, like making objects public or creating a lifecycle policy. Those types of operations are not granted as part of this policy. Let's move on to our fourth example. And this one is relatively short. In this example, we are going to be granting the ability to assume an IAM role, and then with our resource section, we're going to specify that any role in the account is possible to be assumed. We could go through and restrict this to specific IAM role ARNs and even just have a list of them, or we could use not resource if we wanted to restrict further. But this example could be used as just a standalone policy that you associate with users when you want to give them the ability to assume IAM roles. Be careful though, this could actually grant them the ability to assume an IAM role in somebody else's account. So from a best policy perspective, you would not want to provide an asterisk under resource. You would want to explicitly define the roles that are allowed to be assumed. For our final example, this one is also going to come in two parts. And this one's not going to be based as much on technical access, but more on administrative access. In this particular policy, we are granting the ability to access things like billing, account usage, payment methods, and the ability to view budgets across the account. And so by itself, this policy would be great for granting accounting or finance people the ability to view resources in AWS that are directly associated with their jobs. But Is it least privilege? Probably not. When we've defined resources star and we haven't defined any explicit deny statements, we really haven't implemented least privilege. And that's where the second part of the policy is going to come in. Now we have another effect, deny, and we're utilizing not action, and then we specify all of the same actions that we did in the first part of the statement. And so by changing that previous section to deny and not action and providing the same text, we have implemented least privilege. Our accounting or finance users will be restricted to the area that is appropriate to their job, and there's an explicit deny for literally everything else that is outside of that. And this might even be used to provide proof of access compliance for those less technical users who wouldn't be working anywhere else in the AWS account anyway. For this question breakdown, I wanted to give an example that actually provided multiple solutions that are all technically feasible as answers to the question. And so let's walk through the question text, then we'll cover the key terms, and then we'll walk through the different answer choices and determine which one is correct. Your company has recently signed a partnership agreement to share data with another company. The data is stored in an S3 bucket, and the partner is also using AWS. Which of the following are required to configure least privilege access for the partner? Select all that apply. For this question, it's not realistic to see a select all that apply. They will always tell you on the exam how many answers are required to get the question fully correct. And so I've deviated slightly here, but let's walk through the key terms. We're sharing data with another account. We're working within the context of S3, and least privilege is a priority. And so as we walk through the answer choices, we're going to see some things start to stick out. And we're not necessarily going to go through these in order. We're actually going to start with B. Create an S3 bucket ACL on our bucket, granting full access to the partner account ID. This is a possible standalone solution that would meet the technical requirements of granting access. If we look through the answer choices, we'll find that there is another possible standalone solution, which is choice E. Create an IAM user in our account with full access to S3 and send the credentials to the partner. So that's E. That's another possible standalone solution. Neither of these really qualify as far as least privilege is concerned, but let's look through the rest of our answer choices. If we look at A, B, and D, this is a possible multi-step solution. A, create an IAM policy in the partner account, granting access to assume our IAM role. C, create an IAM policy in our account, granting appropriate access to the S3 bucket in question. And D, create an IAM role in our account with a trust for the partner account and an external ID, then attach an IAM policy with S3 access. This is a multi-step solution, and if you look at these three possible choices, only one of the three solutions attempts to handle least privilege, and that is going to be the ACD solution that works with IAM roles, where we're only granting access to the S3 bucket in question. And so the correct answers are going to be A, C, and D. Lesson 8 begins with a focus on different types of identity federation in order to access AWS resources. From there, we move into resource-based access control for different services, and finish up with troubleshooting strategies. The case study for Lesson 8 is a series of examples of broken permissions. For a lot of organizations, it simply isn't reasonable to create a whole bunch of users and passwords and groups and so forth in IAM when they already have an identity provider, usually in the form of Active Directory. And if you're willing to go through the effort to set up ADFS on Active Directory, then you can set up federation with AWS over SAML 2.0. And we can visualize this as a sort of timeline. The very first step is the user authenticating against the local identity provider, again, probably Active Directory. And then the identity provider is going to return a SAML assertion. This is just going to be in the form of text. And at this point, you're going to have to interact with AWS. And you're going to have to make a call to STS, assume role with SAML. Thankfully, when you set up the SAML trust between your AWS account and your ADFS, there is a new URL that is provided where you can simply post the data that's required to this URL rather than making this explicit call. And as part of the payload, you'll have to provide the Amazon resource name of the SAML provider, which is set up within your account, the Amazon resource name of the IAM role that you would like to assume, and then the text of the SAML assertion itself, and this will be the authentication portion. Once that has been received and successfully processed, then the STS service will return credentials back to the requester, where you can then use those credentials to access AWS services. If you used the URL that's provided with the SAML trust to perform this federation, then it also gives you the option of dropping you into the AWS console using SSO. In your study for the certification, you should include some time spent learning Cognito. This is a service that has a couple of different worthwhile use cases, including the ability to federate between mobile applications and AWS resources. But you're going to be expected to understand the details of how this authentication works and how federation works, whether you're using Cognito user pools or Cognito identity pools. And so in this section, we'll talk about the user pools, what they're used for, and in our next section, we'll cover how that is going to integrate and become part of identity pools as well. The first step is that the client is going to send the appropriate credentials for whatever provider you've set up as part of the Cognito user pool configuration. This can be Cognito itself. It can be a SAML provider. It can be a web identity provider, or any OpenID compatible system. From that point, Cognito is going to perform the actual authentication against the provider, and it will manage both the user and directory profile. Cognito user pools do not store any information like usernames and passwords. They simply act as a durable store for this profile information so that you can use them across multiple devices and platforms. The return from the identity provider will be in the form of some type of token that is identity provider appropriate. Cognito will accept these tokens from the identity provider, although it does not store them, and it will then pass those user pool tokens back to the client. So what can you do with these user pool tokens from there? You can use them to access server resources if you want to generate custom code that will accept these as authentication on your application running behind a load balancer. You can use them for direct authentication against API gateway endpoints. And you can use them in trade for explicit AWS credentials. How can we do that? That's going to lead us into our next section. We've discussed what it means to federate and authenticate against a Cognito user pool. Now we need to talk about how you can do similar activities with the Cognito identity pool and how it can be used to provide access to AWS resources. The very first step is going to look similar to a Cognito user pool authentication. The client needs to authenticate against the identity provider and sends identity provider appropriate credentials to the Cognito identity pool. From there, the identity pool is going to authenticate against the back end. If you already used a Cognito user pool, this step is done. You've already received the tokens that are required. But if you're using Cognito identity pools explicitly with your backends, whether it's a Cognito user pool, SAML provider, web identity provider, or OpenID, then you still need to get those user tokens back to the client. Assuming the user tokens have been sent to the client, either through authentication against a Cognito user pool or an identity pool, you can then send them back to Cognito using an API call that is named getCredentialsForIdentity method. This call will then kick off a couple of actions. Cognito is going to call the security token service on behalf of the client with those tokens. And it's going to do so with a predefined policy document that's going to be part of the Cognito identity pool configuration. So it's not going to be possible to just generate arbitrary permissions when using a Cognito identity pool. That policy document does need to be hard-coded as part of the configuration. STS is then going to return those AWS credentials in the form of an access key ID, a secret key, a token that is unique to the client, and then an expiration that is configurable by Cognito and can be set anywhere between 15 minutes and 36 hours. Then Cognito will return those credentials back to the client. And as just regular AWS credentials, the client can use those in any way necessary to access the appropriate AWS services that were defined by that policy document. In order to take advantage of the single sign-on service in AWS, you have to have implemented AWS organizations first. But once you have that in play, then it's possible to use SSO as a mechanism for federating and granting you access to other resources and services. In order to take advantage of this, you have to log in specifically to the AWS SSO console. And you have several different options for how to accept the authentication method. The first of these is to simply request that your user log in to the AWS SSO native directory. This just uses AWS directory service on the back end. Another way to implement the authentication is through federation with AWS managed Microsoft Active Directory. This is just another form of directory services where you've created a standalone forest. It's also possible through this mechanism to set up a two-way trust to an external Active Directory so that you can log in to either of these two directories. Your third option is to take advantage of AD Connector. This is a proxy that forwards any Active Directory requests across either a virtual private gateway VPN connection or direct connect back to an external Active Directory. Once you have authenticated, you can use this authentication to then reach out and use other services, such as other accounts within the AWS organization. When you do this, you have the opportunity to take advantage of console access, as well as the ability to request CLI or SDK credentials in the form of API keys with a 1-hour expiration. Another choice for federation is to take advantage of third-party services that have partnered with AWS to make this possible, like Adobe Creative Cloud or Office 365. The list is large and growing every day. And your final choice for federation is to grant access to custom SAML applications on the back end. So this might be used for an enterprise application that has been designed internal to the company, where you'd like to provide a single entry point, which would be the SSO dashboard, for access to your service. In this section, we move into resource-based permissions. And we're going to start with a really interesting example using AWS organizations. And when you implement AWS organizations, the resource being protected is the AWS account itself. And by using organizations, you have the ability to treat your AWS accounts like an organizational unit in a directory. It gives you a lot of other really cool features too, like the ability to create accounts programmatically. You can invite standalone accounts to join. So let's say your company has acquired another company that is in AWS, and you would like for them to become part of your organization so that you can apply the permissions at the account level. Well, you can do that using organizations. Within the organization structure, you can create what we call service control policies. These look almost identical to IAM policies, and they can be set up for either blacklisting or whitelisting, allowing or denying, but it is at the account level, not at the user level. The master account, the account that was used to create the organization, however, is not affected by any service control policy that has been created, and accounts can only be part of one organization at any given time. So if you look at an organization and the hierarchy of accounts that you create that do look a lot like a directory, it might look something like this, where you have a master account at the root of the organizational hierarchy, and you'll have one or more member accounts in tree nodes that you've created, again, to look like a directory. And this directory structure, it can match your actual company org chart. It can be designed around projects. It can be designed around offerings or workloads or compliance. It is completely up to the customer to make this determination. And so, if you start to apply service control policies, you can specify where in the tree they will take effect. If you apply a service control policy at the root node of this tree, you are going to impact member accounts 1, 2, and 3, but you will not impact the master account whatsoever. If you apply a service control policy at OU2, you're only going to impact member account 2. It will have no impact on the other accounts in the tree. And if you were to apply a service control policy at OU1, it would only impact accounts 1 and 3. One of the most popular services where you'll be expected to know how to implement resource-level access controls is S3. And within S3, you'll have an opportunity to set permissions using either bucket policies or ACLs. So we're going to talk about ACLs first. You can apply an ACL at either the bucket itself or on individual objects. This particular feature has been around for a long time. S3 is one of the elder statesmen of the AWS ecosystem. It was deployed in 2006, and that was long before the concept of IAM or bucket policies were a part of the AWS ecosystem. And so to set permissions early on, ACLs were the only way to make this happen. And so by definition, they're going to be fairly primitive. Because they predate IAM, they're not going to have any concept of IAM resources whatsoever. They don't even understand the concept of an Amazon resource name. They are XML text, not JSON text like the rest of all of the access control mechanisms in AWS. And so you'll want to get familiar with the XML format of these ACLs because they're not going to look like regular policy documents. Now within these documents, you have the ability to apply the permissions to grantees. And a grantee can either be a 12-digit account ID or it can be a predefined S3 group. And there are only a couple of these that are available for selection. Now let's walk through the different ACL permissions and whether or not they apply to the bucket or the object and what that means as far as access is concerned. If you want to set a read ACL on a bucket, that gives the grantee the ability to list objects in the bucket, and that's it. If you want to grant the read ACL on an object, the grantee is given the ability to read object data and metadata. The write ACL is a little different. You can only apply a write ACL to the bucket itself, and this gives you the ability to create, overwrite, or delete any object in the bucket. And so from an object perspective, the write ACL has no impact whatsoever. There's another set of ACL permissions around ACPs. These are the ACLs themselves. And so if you set the read ACL on a bucket, it allows the grantee to read the bucket ACL. And this is that XML document. If you grant this at the object level, then the grantee has the ability to read the object ACL as well. Write ACP, pretty straightforward. When you apply this at the bucket level, that gives the grantee the ability to write the bucket ACL. You want to be really careful with this one. If you simply grant write ACP to the grantee, then they can change it and give themselves the rest of the permissions they might be lacking. And from an object perspective, you want to be careful as well, because this gives them the ability to write the object ACL. Granting full control is exactly what it sounds like. Granting full control at the bucket level means that you get all the permissions over the bucket. If you grant it at the object level, you get all permissions at the object level. There are canned ACLs that you can pick from when you're creating these ACLs, so you don't necessarily have to create these XML documents by hand. You have private, public read write, AWS exec read, authenticated read, bucket owner read, bucket owner full control, and log delivery write. But not all of these are going to be commonly used. In fact, there's only a few of them that you're going to want to keep track of from a certification purpose. First of these is private. That is the default ACL that's applied to both buckets and objects unless you make an explicit change. Next is public read write, and you don't want to do this. If you grant public read write permissions, that means that the grantee can do anything they want with the bucket, and remember, you as the owner of the bucket pay for not only the storage of the objects in the bucket, but also the traffic against those objects. Next is AWS exec read. If you are migrating AMIs that have been created on premises into AWS, this is the ACL you set on the object when you upload it into the S3 bucket so that it can then be transferred into where the regular AMIs reside. And finally, log delivery write. This is the canned ACL that's used for access logging. And an example of where this is used is when you enable access logs for CloudFront. These are applied at the bucket level, and you can only create one per bucket. One benefit of using the S3 bucket policy over an IAM policy is that the bucket policy actually has a longer character length limit than an IAM policy does. It's in the same format as the IAM policy. So all of our strategies that we've discussed for creating an IAM policy will apply to the S3 bucket policy as well. It only applies to the attached bucket. So there are strategies around providing access to multiple buckets where you might use the IAM policy instead and then just specify a number of resources, rather than trying to maintain multiple, possibly identical S3 bucket policies on several buckets. When you create the bucket policy, in the resource section, you still have to define the bucket. The resource section is going to be a required element of this policy document. Next, I'd like to talk about an interesting exception to the access control policies that we've talked about up to this point. And this is an interesting corner case where the rest of our policy evaluation can actually be superseded by a single configuration, and it's called S3 Block Public Access. This is a default on all buckets that were created after November 15th, 2018. And what this means is that you can set a couple of different scopes, either the account level or the bucket level, where public access is guaranteed to be blocked either at the ACL level or the bucket policy level. And what that means to you is that even if you create a bucket ACL that allows public read or a bucket policy that grants read access to all principals, this will take precedence over that and they will still be denied access. S3 block public access can be configured using the CLI. It can be configured using the console. And if you're running into issues where you think you have granted public access to an object and you still can't reach it, you may want to look at the S3 bucket itself, go into the configuration and view the block public access config, look at those Boolean variables to see if they're set or not. There are a lot of services in AWS that provide resource-based permissions, and I chose to provide a couple of examples that I thought might show up on the certification, which would be the API gateway and Lambda functions. There's another big example, which is KMS, but that's actually saved for its own discussion as part of one of the other lessons. So when you create an access policy on an API gateway, you get to specify principals, just like you would with any other IAM policy or S3 bucket policy that we've already discussed. And you can grant access to IAM users. You can also grant access based on source IP addresses or CIDR ranges. It doesn't have to be an explicit principal as the IAM policies require, where it must be an account or a role or a user and so forth. It can actually be a network range. The principal can also be a VPC ID. If you only want your API gateway methods to be invoked from a specific VPC, you can do that directly in the access policy document. You can also provide access directly to VPC endpoints. And this is a really cool feature because you can actually share your API gateway with other accounts, with other customers, and you can even open it up for subscription-based access through the marketplace using this particular feature. Lambda functions also have resource-based access control. And so you can apply an access policy that, again, is in that JSON format with all of the elements that you might expect to a function itself. You can even set up cross-account permissions, and you can do this through the access policy document, or you can grant it directly using IAM roles. So you have options of using user-based permissions as well. If you want to provide cross-account invocation permissions using the Lambda function access policy, you are going to have to require the alias name from the client side. They will need to know the alias of the Lambda function and the ARN to be able to invoke it properly. When you set up permissions on your Lambda function using these policies, you can even restrict the version of the function that can be invoked And this last point was actually news to me as well. A Lambda layer is where you have libraries that are in use as a common framework for multiple Lambda functions. You can share your Lambda layers using an access policy. Now, I'd like to walk through the evaluation when you are applying resource-based permissions to API gateway or Lambda functions. It changes the policy evaluation flow just a little bit because you might not have a traditional principal invoking, say, an API gateway. If it's coming from a site or network range, for example, then there isn't a traditional principal involved there. And so the way this works is you're going to evaluate the access policy on the API gateway method or the Lambda function first. It's going to look to see if that policy document exists. If it does, it's going to look for an explicit deny against the principal. If there is one, they're done. And it doesn't matter, even if they have administrative access to the account, otherwise, they will still not be able to use the resource. If there's no explicit deny, then you check to see if there's an explicit allow in this document. And if there's not, then the implicit deny takes over. But if there's no explicit deny and there is an explicit allow, only then does it begin the next flow to evaluate the permissions of service control policies, IAM roles, and so forth. When it comes to troubleshooting permissions in AWS, from a certification perspective, there are an almost infinite number of possible scenarios and details that you might see on the exam itself. And so I've tried to come up with a couple of general scenarios that they all sort of fit into. The first of these is user cannot perform action X. And then the question will throw out a bunch of scenario details and the conditions under which the user was attempting to perform the work. And then it's up to you to look for root causes that are appropriate in the answer choices. Another one is application cannot contact service Y. And it will provide some details around the environment and the credentials that are being used. The third one is permissions seem to be granted, but they don't actually work. And so in this troubleshooting scenario, you're usually going to be looking at different policy documents and attempting to figure out if they've been misconfigured in some way. There are a number of possible root causes for these different troubleshooting questions, but general strategies for you as the certification candidate. First and foremost, you have to understand the order of evaluation for actions. All of the different policy evaluation conditions and exceptions that we've talked about are going to be in scope on the exam. You really need to learn where deny statements override everything else because all it takes is one. So you need to learn where they can exist to even override administrative access to the account. You need to know which services have resource level access control. We've talked about a few of them, S3, API Gateway, Lambda, and we're going to be spending quite a bit of time talking about KMS. Memorize those condition options. All of those different choices of strings and booleans and IP addresses and if exists, those are in scope. Learn how permission boundaries work. This is an area that seems to be fairly new to a lot of different customers and professionals in AWS. And so understanding that even if the IAM policy allows the user to perform the action, but it isn't within the permission boundaries, they will be denied the ability to perform that action. And in fact, organizations' service control policies are similar. Even if you have administrative access within the account, but the action is not allowed within the organization's service control policy, you will not be able to perform that action. Keep in mind that the API endpoints have limitations where you can be denied access. The first of these we've talked about. A request must be sent within 5 minutes of true time, and if it isn't, it's denied regardless of the access that you have. But there's another one that can show up, and that is if you make too many requests against a specific API endpoint, you can get throttled. And that would be in the form of denying your requests. Different services have different throughput rates that are allowed before you get throttled, and some of these services have limits that you can increase if your company requires that to be able to operate properly. Troubleshooting tools are going to be a list of usual suspects. CloudTrail is a great example where you can look at the audit log of everything that's happened against your account, and if you are trying to troubleshoot an action that was denied, you will be able to pull all of the details around why from CloudTrail. You can look at the Access Advisor reports. You can determine, for example, whether an IAM user has accessed a particular service within a certain time period. CloudWatch Logs Insights. This is a great way to look at those CloudTrail logs in an interactive form where you can query in real time and get results very quickly. VPC flow logs might be required for troubleshooting if you're not positive that your request is even making it to the API endpoint for the service. Another great tool is AWS Elasticsearch with the Kibana dashboard enabled. This is going to give you a Splunk-like interface for web browsing so that you can query objects that are in that Elasticsearch instance. And you have the good old-fashioned command line error output. If you are using the CLI to perform a lot of these operations, there will usually be an error code that is returned when your action is denied. Learn about these error codes and what they mean because they will tend to help you from a troubleshooting perspective. Welcome to the case study for this lesson. And in this case study, we're going to take some examples of broken permissions and show what might be required to be able to fix them. And so our scenario is to be able to recognize permission problems that prevent normal operations. In our first example, we have an S3 bucket ACL, and our requirement was to create a bucket ACL that would allow CloudFront logs to be written to the S3 bucket in question. Notice this is written in XML, so it doesn't look familiar like the IAM policy documents do. But if we dig a little deeper into the policy, we'll find that there's really only a couple of areas that the customer has the ability to make changes in. Most of this ACL is really just static, and even fewer elements are specific to access logs. The owner ID, the S3 group, and the actual ACL that is granted on the bucket are really the only three areas where we would be making changes. The owner canonical user ID is something we can only find from the root account by looking in our account information, and it's going to be much longer than a 12-digit account ID. The URI for S3 groups, these are available through documentation, and then the permission itself is just one of the possible bucket ACL options. Now in our case, logs are not appearing in the bucket. What could be the possible cause? Since there's only 3 places we can make changes, if we look through these, we find as long as our canonical user ID is correct and the URI was a direct cut and paste out of the documentation, the only other option can be the permission. And if we look here, we used the wrong ACL. By setting read permissions, that's not going to grant CloudFront the ability to write logs into the bucket. And so if we simply make that change from one ACL to another, changing it to write, that repairs the ACL and logs will start to flow. In our second example, our requirement is that we'd like to be able to grant permissions to our IAM users that they will be able to rotate their own IAM password when required. And if we look at the permission document that is granted by membership within an IAM group, you can see all of the appropriate permissions are here. We are allowing them to get the password policy. We are allowing them to get user metadata and change the password only for themselves. And in fact, this was an example from our case study in the previous lesson, and we know that this works. So why can't our users change their password? Well, if we dig a little deeper, we find that permission boundaries have been set up for all of our users for common tasks. The ability to perform work in S3, CloudWatch, EC2, DynamoDB, common services. This is the permissions boundary. If the IAM policy is permissive, but the permissions boundary does not have an explicit allow for the same action, they will not be able to perform the work. And so, one way to fix this is by taking the three actions, IAM get account password policy, IAM get user, and IAM change password, and adding these to the permissions boundary so that they have an explicit allow that matches the policy that's applied through the IAM group membership. For the third example, I'd like to go through permission possibilities when you have a combination of permissions between service control policies through organizations, IAM policies, permissions boundaries, resource policies, and then determine whether or not we will be able to perform the work. And in our first example, we have explicit denies at both the service control policy and the IAM policy. The behavior is going to be deny regardless of whether we have a permissions boundary or resource policies. Our next example is if we change the service control policy and the IAM policy to allow. In this case, the behavior will be to allow the action if there is no permissions boundary and no resource policy. If we have an allow at the service control policy, but a deny at the IAM policy, that explicit deny is going to take precedence and we will not be able to perform the action. If we have an explicit deny in the service control policy and an explicit allow in the IAM policy, we still can't perform the action because the explicit deny takes precedence. If we have allow statements in the service control policy and the IAM policy, and a permissions boundary that exists without an explicit allow, we are not going to be able to perform the action. And our final example is if we have allow statements at the service control policy, the IAM policy, and the permissions boundary. If there is no resource policy, we will be able to perform the action unless we are using KMS. That is going to be a notable exception, and we're going to be talking about that in an upcoming lesson. Welcome to the question breakdown for this lesson. I wanted to choose a question that required a little bit of operational knowledge of how to actually do the work behind the scenes rather than just understanding strategically how to get the job done. Your company just completed an acquisition, and the acquired company has an AWS account with resources that cannot be migrated to your existing account. How can your IT department manage account access and permissions across both accounts most effectively? Let's look at our key terms first. We have AWS account that is part of the company that we acquired. They can't migrate their resources, and yet we would like to be able to manage access to their resources without expending a lot of extra energy. So let's walk through our answer choices and see if we can figure out which one of these makes the most sense. Answer choice A, enable AWS organizations on the company account, and then invite the acquired account to join, and then manage both using AWS SSO. This takes care of all the requirements. It covers permissions, it covers access, and they both happen from a central location. It might be the right answer, but let's look at the other options first. B, manage both accounts using cross-account IAM roles for IT administrators. This answer covers permissions and access, and technically it works, but it's going to require management overhead in both accounts, and it's not going to be as effective as answer choice A, although it does technically get the job done. How about C? Enable consolidated billing on both accounts and configure cross-account IAM roles. This is similar to B, but consolidated billing is irrelevant. That doesn't give us the ability to manage both accounts from the same place. It just makes it so that we're paying from one location. But as far as permissions management, that does nothing for us. So let's look at D. Configure SAML federation for both accounts with your existing AD organization and use that for single sign-on. This meets the requirements almost as well as A does, but it also requires effort in both AWS accounts to configure all of the IAM roles, and so it's not going to be as effective as A. And therefore, our correct answer for this question will be A. Module 6 is made up of 2 lessons covering the 5th and final exam question domain, data protection. Lesson 9 is all about key management for encryption and authentication. In Lesson 10, we discuss data encryption methods, both at rest and in transit. In Lesson 9, we will discuss different services used for managing encryption keys. From there, we cover keys for authentication and proceed into a discussion of key management troubleshooting. The case study for this lesson is a walkthrough of enabling server-side encryption for CloudWatch logs. This final question domain covers an awful lot of ground. And so let's walk through the main points that are listed on the AWS site for this question domain. First, awkward sentence, design and implement key management and use. There are so many services that will encrypt your data at rest that this is going to be a big focus for your study. Troubleshoot key management. This is where you're going to want to dig into the details and actually do this in your own accounts so that you can learn how easy it is to break and how difficult it can be sometimes to fix encryption solutions. And the third point is design and implement a data encryption solution for data at rest and data in transit. This is going to, again, cover a lot of different areas. It's going to be storage, it's going to be application infrastructure, and it's going to require you to have a lot of architectural and operational knowledge within AWS. First, though, let's cover one of the basics. There are 2 primary types of encryption: symmetric data encryption and asymmetric data encryption. Asymmetric data encryption requires 2 keys, one for encryption, one for decryption. And this is how RSA key pairs work, SSL, TLS, and so forth. And we're going to talk about those in our next lesson. But for symmetric data encryption, it's a good idea to review exactly how this works, because once you understand this workflow, it makes it a lot easier to understand the basic premise behind encrypting data at rest within the services of AWS. And so we're going to start with a generic application. This could be custom code. This could be a service within AWS that stores data where you've enabled or configured data encryption. And the first step is the application or service is going to request a new data encryption key from the key management infrastructure. Now, I've used the icon for KMS, but it could be any key management infrastructure, even one that you have created as a custom element of your infrastructure. The key management infrastructure then returns 2 elements in the payload of the response. The first of these is the plain text encryption key, and the second is that same encryption key that has been encrypted using a master key. The client or application will then use the plaintext key to encrypt the data object. And at least as of today, you only have the option of AES 256 across the AWS ecosystem. From that point, the application will then place the encrypted data in storage, and it will attach the encrypted data key as metadata, and it will purge the plaintext data key from memory entirely. So it is now completely gone. Now, one thing to keep in mind, the key management infrastructure, depending on which service you're using, may or may not actually store those data encryption keys. In the case of KMS, that we'll be talking about in just a little bit, it does not store them at all. So when you place them into storage alongside the data object, you'll want to make sure that they are being stored durably. Now, when it comes to decrypting the object, the application will request the encrypted data key from storage. Now, remember, this is stored as metadata alongside the object. Then, once it's received that, the application will send that encrypted data key to the key management infrastructure. And assuming that the application or client still has permissions, the key management infrastructure will decrypt that data encryption key and send the plaintext version back to the application. The application can then decrypt the data using that plaintext data key and then simply purge that data encryption key from memory. And depending on the storage service that you're using, that data might still be in storage with the encrypted data key attached as metadata, or depending on the service, if you extract it from storage and then delete it, when you want to encrypt it again, you would require new data encryption keys. So let's talk about a couple of considerations when discussing symmetric data encryption, and these are going to apply to all of the various services in AWS where you can store your data at rest and encrypt it using the symmetric data encryption options. First question is, what keys are involved? How many keys are involved in the chain of trust, and where are they going to be stored and who owns them? So we have the root CA. This is going to be at the top of the chain. We have a master key that is then used to encrypt the data encryption key. And ownership of these keys is going to be very important. And we'll have some choices in AWS depending on the service that we use. It could be AWS owning the key. It could be the customer owning the key. Or it might even be a third party who has ownership of one of the keys in the chain. There are other considerations that you want to keep in mind to help you select the correct services and to understand how they work. The next question will be, where is the encryption actually performed? Is it done on the server or service side? This is great because it means that you're offloading the CPU overhead of encryption directly to the provider. But the drawback is that you are relying on the service or provider to actually do this reliably and securely. Is it performed on the client side? There might be benefits here too. Depending on how strict your security requirements are, this may be your only option. And our next question is, how is the key access control implemented? Is this going to be done from a user perspective, where users are simply granted access to the service and able to use all keys? Or is it going to be based on a specific resource, either at the master key context or at the encryption key context? And even within AWS, the solutions are going to vary as far as the access control. The next topic is, what services are even available for use within AWS? And from a certification perspective, it's going to be important to understand what services are out there and how hard they're going to be pushed on the exam. The first one, and the most popular, is going to be KMS. We're going to be spending a bunch of time talking about this coming up. After that, we have Cloud HSM. This is less popular, but it has some niche use cases where you might be forced into using it. The AWS Certificate Manager is another way to manage keys, and this one's going to be used for asymmetric data encryption only. It's possible to launch off-the-shelf products using the EC2 marketplace and manage them on your own even while you're using a third-party product. And finally, there are a lot of organizations that simply choose to do it themselves or to bring a custom solution into AWS having been launched onto an EC2 instance. My recommendation for your study time being spent in the right places for the certification, you should concentrate on KMS and Cloud HSM and spend a lot less time on other possibilities. KMS is one of the few services that I decided deserved a full introduction, even though the exam itself is at more of a professional level. This service is not commonly well understood, even by those who have been working in AWS for years, and so we're going to give it the full treatment. KMS stands for Key Management Service, and it's going to be used for symmetric data encryption across the AWS ecosystem. It is a region-scoped service that is fully fault-tolerant and highly available. It is also multi-tenant, which may have security ramifications depending on the requirements of the particular organization. Within KMS, there are a couple of primary workflows. You have the ability to generate and store customer master keys. You can upload master key material from on-premise, if you like, and you can generate data keys. It is really important to note that KMS does not actually persist data keys. It can generate them, it can encrypt them, and it can decrypt them, but it cannot store them. And so, when you're working with KMS, it's going to be up to the client or the storage solution for the data that's been encrypted to actually persist the data encryption key. There's another thing that KMS does not do. It does not encrypt data. So the data encryption is going to be offloaded to either the client that is requesting it or the storage layer itself. It's possible to use KMS with a custom key store. When you do this, it actually takes advantage of Cloud HSM on the back end and changes the service from multi-tenant to single tenancy. This is a nice way of getting the best of both worlds. You have a single tenant storage of your keys, but you have a service with full integration across the rest of AWS. It is also FIPS 140-2 validated for those of you that are working in the public sector here in the US. Let's talk about the CMK. That stands for Customer Master Key, and this is where a lot of the operations are going to be happening within KMS. A CMK is a logical object. You can think of it as a container that is associated with configuration, access control, and then the backing key material where you can have one or more of those backing keys. From an operational perspective, there are a couple of primary tasks that you're going to be doing within KMS from a management perspective. You can create new backing keys for your customer master key. You can also upload backing key material. So if you have a key management infrastructure on-premise that you want to use to generate all of your master keys, you can do that, upload the backing key material into KMS, and then use it to encrypt your data at rest across AWS. You can rotate your backing keys on demand. So this can be done using the command line or through the console. You can also rotate backing keys on a schedule. Now, AWS does not give a lot of flexibility, and at least as of today, when you set up backing key rotation, the schedule only allows for once a year rotation. If you want to do something custom, at least today, you'll have to do it using an on-demand mechanism and then schedule that using some other service. Rotating the master key backing material is going to be one of the most common activities performed within KMS. And the steps look like this. First, you create the new backing key in the customer master key. So now you have two key IDs that are available within this customer master key. You will never be able to view the backing key material in plain text. Even if you uploaded it from an on-premises solution, AWS does not give you any feature that allows you to view the master key backing key material. So once you've created that new master key and you have two key IDs, the old backing key material is still going to be used for decrypting old objects. It's still going to be used for decrypting those previous data keys. But if you're in a situation where you suspect that the backing key material has somehow been compromised, you can choose to delete it. When you do this, any object in storage that was encrypted using that key ID 1 is no longer going to be accessible. There is no way within AWS for you to decrypt that data in any other mechanism. So once you create that second key ID, or if you have multiples of them, the latest one is used for encrypting and decrypting data keys from the time of rotation. Let's look at another workflow which uses a feature called CMK aliases. If you have an application where you'd like to hard code the Amazon resource name for the customer master key, and you don't want to worry about which backing key material is currently being used, you can do this with aliases. And in fact, an alias will point to a customer master key itself. If you want to use multiple master keys over time, this is a great way to reduce the amount of operations required from the application side when you make changes. So you create an alias using the command line, and then you can use that alias after it's been pointed to an existing customer master key. What if we have a suspected key compromise, but we need our application to continue functioning? We need it to continue being able to encrypt data in storage. What we do is we create a brand new customer master key. Then we can configure the access control for this second CMK to match CMK1. Our next step is to update the alias that was formerly pointing to CMK1 and point it to CMK2. This is as simple as a single command using the CLI. Once we've done this, our application will now be using CMK2 going forward, and we can then perform the rest of our security incident response operations. We can update CMK1 access control so that the application cannot access it under any circumstances. And then, once we've performed the rest of our forensic analysis, we may choose to disable CMK1 when it is appropriate to do so. Access control for the KMS service might be one of the single most important niche topics that you should study for on the exam. It's not a question of whether or not you will see this as a topic. It's a matter of how many questions you're going to get that are directly related to it. And so it's really important to understand not only the choices that are available for access control in KMS, but also the guidance from AWS on which types of access control are most appropriate for different scenarios. The first of these is IAM, and this is going to be a topic we've already discussed. It's user-based access control using IAM policies and granting access to the KMS service through this mechanism. And so this is going to be appropriate for generic access to the service, for management and some operations. This is what you're going to grant if you want to be able to create new CMKs for an upcoming project, or to be able to audit usage of existing resources within the service, or even to inventory the existing CMKs to figure out what you have, how often they're being used, and how much you're being charged for the usage of this service. This is where IAM is going to be really powerful. But you have choices. And there are really 3 different ways to go about access control in KMS. The first of these is by using key policies for almost everything. Second is to use IAM in combination with key policies. And the third is to use key grants in combination with the key policies. And only the first of the 3 is absolutely required. When you create a CMK, you are forced to create a key policy. You don't have any choice in the matter. But the other 2 are optional. You do not have to create explicit IAM permissions for management of KMS or usage across services or even from custom applications. The key policy can be used almost as a standalone access control mechanism. So let's talk about those key policies, since you absolutely have to create one. When you walk through the console and create a new CMK, the wizard forces you to create a key policy along with the rest of the information for the CMK. And so key policy basics are going to be like this. There's no default root access. This is really interesting. So this means you create a CMK and by default, the root account doesn't have the ability to use the CMK. The root account does have the ability to change the key policy to grant themselves access. But by default, if you create a CMK, the root account cannot use it. There are different types of principles for this resource-based policy, and it does look a lot like an IAM policy with a lot of the elements that we've discussed in the previous lesson. It's going to include IAM users, IAM roles, 12-digit account IDs or ARNs of accounts, and other services so that you can provide cross-account access and cross-service access directly in a key policy. Now, the key policy is going to be broken up into a couple of sections, one of which will be key administrators. And if you're doing this through the console, it will ask you explicitly to identify the key administrators. These are going to have the ability to create or delete the backing key material. They can create or revoke key grants that we're going to talk about coming up. They have the ability to describe the key metadata and to look at the metadata tags that have been applied to the resources. And the key administrator, very importantly, has the ability to delete the key. From a security or resilience perspective, you might choose to disable that last piece so that even a key administrator has no ability to delete the key directly. You might rely on other mechanisms for this particular workflow. Key users are where all of the encryption and decryption work is actually going to get done. So they're going to have the ability to invoke the workflows for creating new data keys, decrypting data keys, and even re-encrypting data keys. This is an interesting one. Most services give you the ability to re-encrypt the data at rest using a new backing key. This is a nod by Amazon to recognizing that as KMS becomes more mature and customers have been using it for now years, they're going to want to be rotating those backing keys and eventually removing old backing key material. This isn't possible unless you re-encrypt the existing data in storage. Key users are going to be able to create new data keys, they're going to be able to describe data keys, and they can even delegate a subset of their own permissions using grants. So we're going to talk about grants in just a few minutes. I'd like to show you an example of a key policy where this might be in use for enabling server-side encryption for a CloudWatch log group. In this particular statement, you're going to see it looks a lot like an IAM policy. We're going to have an effect, a principle, an action, and a resource. We're going to allow the CloudWatch logs service that's listed as logs. Whatever region we're in, .amazonaws.com, and we're going to give the abilities to perform encrypt, decrypt, re-encrypt, generate data key, and describe on all resources. Now, resource star just means that CloudWatch logs will be able to use this particular CMK. It does not grant access to all of our CMKs. Our second example is going to enable the auto-scaling service to launch instances using encrypted EBS volumes. And this one's going to be long enough that it requires two parts. The first part is we're going to allow a principal that is a service role for auto-scaling. Remember, we've talked about service-defined roles that can sometimes be created the first time you use the service. Well, this is an example of one of those for auto-scaling. And we're granting it the ability to encrypt, decrypt, re-encrypt, generate data keys, and describe keys on the CMK. But this isn't the only action that we need to allow. We also need to allow that same principle to create grants so that the EC2 instances that are being launched have the ability to use the data on those EBS volumes. So we have two workflows. One is to create the volume itself with encryption enabled. The second one is to delegate permissions to the EC2 instances that are part of the auto-scaling group so that they can use these encrypted volumes as well. Let's talk about grants. A grant is going to be used for very different reasons than policies. This is where you're delegating temporary permissions that might have an undefined lifetime. And for these, you can only allow, there's no deny possible. And that makes sense from a workflow perspective, because if you're delegating permissions, you would only be doing so for the reason of giving them access to some of the resources that you're working with. This is not going to be a recommended use case for key management. And that particular phrase is going to be very important from the certification perspective. You might actually get questions where you are asked what type of access control is appropriate given a particular scenario. Grants are not appropriate for key management purposes. They're used almost exclusively for encryption and decryption. You have the ability to revoke these at any time, which is great for that temporary use case, especially for applications that are going to be granting client-side access to be able to encrypt or decrypt objects. Now here's what it looks like when you delegate. So delegating, or the creation of grants, can be done either from the key policy perspective or within a grant itself. So an application could create a new grant for a client or some subtask and give it the create grant permission. From there, that application can also create grants as long as they have a subset of the permissions that it was granted. The delegation of a subgrant is a great use case for an application that needs to delegate the ability to encrypt or decrypt for one specific data encryption key. Cloud HSM is going to be the second encryption service that you're going to want to focus your study on for the certification, but it's not going to be nearly as well represented on the exam as KMS. Cloud HSM actually comes in two different flavors. And the current version, which is V2, is a dedicated generic HSM that is provisioned on the customer's behalf when they decide to use Cloud HSM as a service. The original version, or Cloud HSM Classic, is actually SafeNet technology, where the Luna appliance is provisioned on behalf of the customer by AWS. This is an availability zone scoped service, So for those of you that are architects in AWS, this should set off all kinds of warning bells that the resilience or high availability of this particular service might be in question or might require a little extra work. It is a single tenant offering, and that's the biggest difference between KMS and Cloud HSM. If you require single tenancy, this might be the solution to choose. It is also FIPS 140-2 validated, like KMS. The different tasks that you're going to be performing with Cloud HSM look like this. You can generate and store master keys. Sounds a lot like KMS. You can generate and store data keys. Here's another primary difference. Cloud HSM allows you to store the data keys within the appliance. KMS does not. KMS relies on the data storage service to store those data keys there. It can also perform encryption within the Cloud HSM appliance. This is another difference. So you can perform bulk crypto on Cloud HSM where it's not possible with KMS. There are some specific workflows within AWS where you don't have the choice to use KMS. The first of these is the enabling of TDE within the RDS service if you're running the SQL Server engine. Cloud HSM is the only way to generate and use these keys that it integrates directly with RDS. Same goes for TDE for RDS Oracle Server. It's important to note that these are the only two engines for which you can enable TDE within RDS. If you want to perform the high-performance bulk crypto, Cloud HSM is a great option for this. If you want to use a PKI, a public key infrastructure, where you are doing asymmetric data encryption alongside your symmetric data encryption, Cloud HSM can perform that as well. And if you want to enable Redshift database encryption, where the customer owns the entire chain of trust, all the way from the data encryption up through the database and cluster level encryption, Cloud HSM is your only option there as well. There are considerations for using Cloud HSM though. First of these is if you want to take advantage of Cloud HSM Classic where it's deployed into a single AZ and using a single device, that's going to require some extra architecting from the HA perspective to make sure that your architecture is resilient. And the recommendation from AWS is that you actually deploy 2 or more of the appliances if you're going to use Cloud HSM Classic. The CLI for Cloud HSM only gives you functions for managing the HSM itself. The CLI does not give you the ability to perform encryption or decryption. You're going to have to use the API directly. And the final consideration is that Cloud HSM Classic is very expensive. In order to deploy a single appliance, the customer has to pay $5,000 up front, along with the hourly usage rate. It's far more cost-effective to go with Cloud HSM v2 if you're going to require that hardware-backed single-tenant solution. But there is also the option to use KMS where you integrate it with Cloud HSM and use that to store your backing keys. The AWS Certificate Manager is an extremely simple service with a very small number of workflows that are possible. This is a great service for you to be able to test out and learn in a very short period of time. And it is in scope for the exam, but thankfully, there's so little that goes into this service that it's easy to learn. The service itself is used for generating asymmetric data encryption certificates specifically for web services. It is region scoped. And from an operational standpoint, This should automatically tell you that you're going to have to create certificates in multiple regions if you want to use them in multiple regions. It is multi-tenant. There is no possibility today for using Certificate Manager in a single tenant situation. And it gives you the ability to create a private certificate authority if you want to go that route. If you would like ownership of the full chain of trust for your SSL certificates, this will make that possible. So the types of operations that you would be performing with Certificate Manager: first, most obvious, provisioning your certificates in the first place. Remember, this is on a per region basis. And so if you want to use them in multiple regions, you'll have to provision them in multiple regions. You can upload your custom certificates. When you create a private CA, you can do it there, but you can also upload them just generically into the service. And you have to manage certificate renewal. Thankfully, this is as easy as a single click within an email, and you don't have to make any changes within the services that are using the certificates when the cert is updated. You can only use your certificates within the AWS ecosystem. Because it doesn't give you the ability to download the certs, you can't use them on EC2 instances or any other customer-managed resource. The services that are in scope for Certificate Manager, and this list may change. You always want to check the most recent documentation. First off, CloudFront. This is the only global service that takes advantage of AWS Certificate Manager. And for this, it actually pulls the certificate out of IAM rather than ACM directly. The Elastic Load Balancer. You can create listeners on all three load balancer types that utilize SSL or TLS, where you can associate your ACM certificate. And finally, the API Gateway. For this service, you can associate the ACM certificate with your particular stage of an API gateway that you've deployed. The certification exam is also going to be requiring background knowledge for candidates for the rest of the AWS ecosystem, anywhere else keys are used. It's not just about encryption of data at rest or in transit, but in many cases, keys are used for authentication. And so the storage of those keys, the management of those keys, and the recognition of where they can be used is going to be important. The most common of these is going to be an EC2 key pair. These key pairs are region-scoped resources, and they're just RSA key pairs where you can create this key pair entirely in AWS. And when you do so, you get one opportunity to download the private key, and then it stores the public key as the key pair metadata. You can also create a key pair locally and upload the public key material into AWS if that is your preference. From there, the key pair is associated with an EC2 instance. And if you're launching a Linux operating system, then the public key is actually installed on the instance itself, and that can be used for authentication against an administrative account on the instance. If you're launching a Windows instance instead, the administrator password that is generated randomly is then encrypted using the public key, and you have to use the private key to decrypt it to be able to log into your Windows instance for the first time. Another service that uses key pairs is code commit. And this one is interesting because it doesn't store the key pair in the code commit service. It's actually a global resource that is stored in IAM and associated with specific IAM users. So with code commit key pairs, You can create them and upload into AWS, but it's only used for authenticating against the code commit repositories. At least as of this time, this key pair cannot be used for any other service within AWS. Now, as far as storing and managing keys, there are a couple of different mechanisms for doing this. And the first is the AWS Secrets Manager. This is part of the SSM service, and it allows you to store key value pairs for custom applications or database connection strings for authenticating to services like RDS. And this has a lot of really cool use cases where if you have an application, every time it launches, it needs to be able to connect to a database, and you don't want to store that connection string with embedded user and password locally on the instance, you can simply extract it from Secrets Manager, and that way when you rotate the username or rotate the password, Secrets Manager will always have the latest version. Another way to store keys would be to use the AWS Parameter Store, and this one is a little bit more generic than Secrets Manager. It's also part of SSM, but it allows you to store different types of text, whether it is structured, like a key pair or a configuration file, but it also allows you to store arbitrary unstructured text that might be a password or a serial number or some sort of key that you would like to use from multiple locations. All right, it's time to go through some troubleshooting examples because these can be representative of scenarios that you could see in the exam itself. The first scenario is a service in AWS cannot access KMS for encrypting objects. There are a couple of possible causes for this situation to occur. And notice I only said encrypting. We're going to talk about decrypting in the next example. The first root cause might be that the key policy, while it was in existence and functional, it got modified so that it no longer works. It could be an existing key grant has been revoked. It could even be due to a change in an IAM policy that no longer allows access for the service to that CMK. The second example is going to be similar to the first, but we have a couple of different root causes. For this scenario, it's going to be a service that cannot access KMS for decrypting objects. And our possible causes, while we have some similarities, like the key policy being modified, it could also be because the CMK backing key was deleted. In that case, encrypting objects might still work fine because there's a new backing key, but decrypting objects might be broken. It could also be because the key grant was revoked or an IAM policy being changed. So there are some key differences, pun intended, between encrypting and decrypting objects and when they break, what the root causes might be. Our third troubleshooting example is going to be based on Cloud HSM instead of KMS. And in this scenario, a service cannot access Cloud HSM for encryption or decryption. And so our possible causes might be that the HSM appliance failed altogether. If you've deployed a Cloud HSM Classic SafeNet Luna, if that appliance failed and you didn't deploy your infrastructure in a highly available fashion, you might have a completely broken encryption infrastructure. It could be based on a change in security group rules. Because the Cloud HSM appliance is deployed into your VPC, security group rules are going to apply to it. It could be that your HSM appliance is simply overloaded and you need to provision more and load balance across them to restore functionality. Our next example is going to be based on a service that cannot access a secret through Secret Manager or Parameter Store for application authentication. And our root causes here might be that the secret was actually deleted. This is where you want to have some kind of assurance within the service that deletion cannot happen except under approved circumstances. The secret-based resource policy might have been modified so that while IAM was working fine, the secret access policy was not. It could be based on access control, where the resource-based policy attached to the secret was modified so that the service or client can no longer access it. It could even be based on an IAM policy being modified if you were using an IAM role for access to the secret. Welcome to the case study for this lesson. And for this one, I wanted an example that was a little bit more operations and a little bit less architecture so that we could walk through each step required to implement a requirement. And for this specific scenario, it's going to be how to implement log encryption on the server side in CloudWatch using a key from KMS. And so our individual tasks that we're going to need to perform are going to be creating the CMK in the first place, configuring the server-side encryption on a newly created CloudWatch log group, and finally, how would we go about troubleshooting an issue related to CMK permissions? So to get started, we have a brand new CMK. And when we implement this, using the dashboard, there are a number of input steps where we are required to come up with information, like an alias name. Creating an alias along with a CMK is a great idea so that you can refer to the alias rather than specific CMKs. We also provide a description for the CMK, and this is where you want to be descriptive. Talk about the data being protected, maybe the level of classification that your company has applied to it. From there, you want to make sure and you add tags. Tagging your resources in AWS is one of the most important things you will ever do. And you can create up to 50 tags that apply to this CMK. So go overboard. Provide the data classification, the application name, the cost center, the environment, the business unit, the owner, anything else you can think of that makes it easier to be able to refer to these resources by those tags, and especially from a billing perspective. Then we get into creating the key policy, and one of the steps that you can take is to disable key deletion by key admins. For a service like this, where we are going to be encrypting logs and CloudWatch logs, this is going to be critical. Make sure you do this. And for most keys, when created, it's good guidance to disable that key deletion by key admins. When we've created the key, we get to copy the key ARN from that newly created CMK. We're going to need that coming up in just a little bit. We also need to grab the key ID. Remember, there is an Amazon resource name for the CMK, and there are key IDs within the CMK that identify the specific backing material that are used for the encryption. Now, we go back and modify the key policy so that we add permissions for CloudWatch logs. And that's going to be in the format of logs.region.amazonaws.com. And let's say in our scenario, we already had a snippet of JSON available, and we just copied and pasted it without really reading the text of the document. Now, we get to create the CloudWatch log group. This is pretty simple. If we're doing it through the dashboard, you just provide a log group name and you're done. But if you want to enable server-side encryption, you're going to have to provide more than that. You're going to have to provide the KMS key ID and the alias ARN. Both of those are going to be required when you enable server-side encryption on a CloudWatch log group. It might be inconvenient, but there is no console equivalent. You're going to want to have the CLI handy in order to be able to enable server-side encryption on an existing CloudWatch log group, or to create a CloudWatch log group with server-side encryption enabled all in one step. Now that we have the log group created, it's been associated with the CMK, what next? Well, logs start to flow. Guess what? They're not encrypted. When we describe the CloudWatch log group, it does not have that CMK associated with it. So what could have possibly gone wrong? One thing we could try and do, since we just started, is to delete and recreate the log group just like we did the first time to make sure we followed the instructions correctly. We do that a couple of times, doesn't really make a difference. They are still not encrypted on the CloudWatch log side. So what else could be the problem? Is it possible that permissions are the issue here? And in order to look at permissions, we have to dig into that key policy again. When we look at the key policy, we dig through the details, we find effect allow, principal service, logs.region.amazonaws.com, and then the specific actions and the resource of star. What we realize, though, is that region was taken out of a template. It doesn't actually have the region name where we've deployed both the CMK and the CloudWatch log group. And so our immediate mitigation strategy would be to change the key policy in line so that we have modified that region to be correct based on where we've created both the CMK and the CloudWatch log group. And as soon as we do that and we test the logs that are written to CloudWatch logs, they are now correctly encrypted. Welcome to the question breakdown for this lesson. And for this question, I wanted to provide a scenario where the answer choices have multiple details in them. So let's read through the question, then we'll look at our key terms, and then we'll go through the answer choices one at a time to see if we can figure out which one's going to be right. An application has a requirement to store data locally on EC2 using encryption. The objects must be encrypted using unique data keys, and the application must be able to delegate permission to each client to decrypt the object once it is transferred to the client. Which solution meets these requirements in the most secure and efficient manner? So when we look at the key terms, there's a number of them that should stand out. We're going to be storing data locally on an EC2 instance, which means probably an EBS volume, but encrypting the EBS volume isn't a solution that is in scope because each object has to be encrypted using a unique data key. From there, our application also has to be able to delegate permission to each client so that when they extract this data from the EC2 instance using the app, they should be able to decrypt it locally. And so we're going to look through these solutions and see if we can find one that meets all of our requirements while doing so in the most secure and efficient manner. First, let's look at A custom key management solution where all workloads are handled by the application. This is going to be a lot of overhead. It's not necessarily going to be fully secure, not necessarily going to be highly available, and we're not sure how the application is going to delegate permissions to the individual clients to be able to decrypt their data locally. Let's look at B. Use KMS with an IAM role for the application, a KMS key policy for the application, and KMS grants for clients. This one does actually meet all the requirements. The IAM role for the application will allow it to create and modify backing keys as required. The key policy for the application allows it to encrypt data and generate new data keys. And The KMS grant for each of the clients will allow them to download the data and then decrypt them without offering any capabilities to download and decrypt somebody else's data. Now that we have the right answer, let's go ahead and look at the other options so that we can make sure we understand why they are incorrect. C first. Use Cloud HSM and built-in permissions for both the application and the client. This is going to be secure, but it's going to be a huge amount of overhead to manage individual permissions for each client. Let's look at D. Use KMS. So it's going to be similar to B. Let's set up static credentials for the application, maybe through an IAM user, and then an IAM role for the clients. This sounds like a decent answer. And if all you did was skim through the documentation, this might be your choice. But we have some problems with this particular answer. It does not meet the delegation requirement. That IAM role for clients would allow the clients to be able to decrypt any data that they were able to download, which would go against our security requirements in the first place. And so the correct answer for this question is going to be B. Lesson 10 will detail several options for data encryption in AWS. We'll start with encryption for data at rest, listing services and how data is encrypted using keys from various sources. After that, we'll discuss encryption for data in transit. The case study for Lesson 10 is an implementation of end-to-end encryption for an application infrastructure. If you were to look through the AWS documentation, you would have a difficult time finding a single doc that has a list of all the services that perform a certain task or have a certain property. And so it takes a little bit of time, understanding, to learn where to find details about the services and to understand, based on the character of the services, whether or not they might have certain properties. In the context of the certification, you're going to be expected to know which services encrypt their data at rest by default with no option to turn it off. And again, there's no single document in AWS that shows this. And the number might be growing over time as new services and features are offered. So you always want to look at the current landscape of AWS and the services that are provided to make sure that you're fully up to date. I've provided a list that should be current as of today, but this list could expand at any point. We're going to start with Glacier, where data is stored in vaults and archives in a way that is similar to S3, except that server-side encryption on Glacier is enabled by default. You can choose the key from KMS that you'd like to use. Snowball is also encrypted by default. The Snowball service are the appliances that you can ship back and forth between your on-premises data center and AWS so that you are not transmitting your data over a wire. CloudTrail is encrypted at rest by default because the storage for CloudTrail is actually S3. When you configure CloudTrail for the first time, it will automatically enable server-side encryption, but you do have a choice as to which keys to use. The storage gateway will always encrypt your data at rest by default, even though your data may be stored locally in your data center. DynamoDB now encrypts data at rest by default. This is a great example of a service that formerly did not encrypt your data at rest by default. And then they released the feature that allowed you to do it, and then they announced that all DynamoDB tables would be migrated to server-side encryption. Elasticsearch is one of the newer services that encrypts your data at rest by default. But it's not the only new service out there, because there's also FSX, for both Lustre and Windows that encrypt your data at rest by default with no option to disable it. Now that we've talked about the services that force you to encrypt your data at rest, we're going to go through a number of different types of services within AWS that give you the option to encrypt your data at rest. And we're going to start with file systems and object storage. The first offering here that gives you that optional encryption at rest is EFS. EFS is the service that allows you to create file systems at a region scope and then expose them to your compute resources in the VPC as NFS mounts. EFS is the region-scoped service where you can create file systems and expose them inside your VPC as NFS shares. EBS volumes have been around for a long time. The ability to encrypt them as an option has been around for a long time. In fact, you can use your KMS customer master keys when you create an EBS volume in order to encrypt it. S3 has a number of different ways for encrypting your data at rest, including the ability to choose keys that are managed entirely by AWS, managed entirely by the customer and uploaded when you upload the object, or to use keys out of KMS, where AWS owns the root of trust and the customer owns the master key and the data encryption key. Each of the database offerings by AWS will also give you the ability to encrypt your data. We already talked about DynamoDB, where it does it by default. RDS allows you to encrypt your data at the storage layer, similar to an EBS volume. Redshift gives you multiple encryption options for the cluster and the database, where you have the ability to choose from different keys as well. Elasticache, if you choose the Redis engine, not Memcache, also allows you to encrypt your data at rest, even though it's an in-memory data store. DocumentDB, with MongoDB capability, also allows you to encrypt your data at rest as an option. And finally, the Neptune graph database gives you this feature as well. There are a number of messaging services within AWS, and gradually these have been changed so that they all allow server-side encryption. When you create a message queue in SQS, you have the option of enabling server-side encryption and then choosing a key out of KMS to use for that encryption. When you create an SNS topic, you're giving similar options for encrypting your data at rest. And finally, with Kinesis, both Firehose and data streams, you have the option of encrypting your data while it is stored in the Kinesis service. There are other services that don't necessarily fall into the same category that also give you the ability to encrypt your data at rest. We've talked about CloudWatch logs in the previous case study, so you're already aware that that allows server-side encryption, but it's not a default. The SSM parameter store feature gives you the ability to encrypt individual parameters on the server side at rest. And the AWS Secrets Manager, also part of SSM, gives you the ability to do server-side encryption. I'd like to walk through the exact steps that are involved when enabling at-rest encryption on a resource in AWS. We're going to use a data volume in EBS as our example, and understanding how all of the different components interact with each other will help you on the exam, especially when you get the more difficult scenario-based questions. So when we first create the EBS volume, whether we're doing this through the console or the command line, we can choose to enable encryption by specifying the CMK key ID at volume creation. And when we do this, the EBS service is going to reach out to KMS and request a new volume encryption key. KMS is going to return two elements with the response payload. One is going to be the plain text volume encryption key, and 2 will be the encrypted volume key using the customer master key. EBS will encrypt the data at rest using the plaintext key, and it will store the encrypted volume key in the metadata for the volume. Now, if we stopped here, we'd be done. If we don't attach our EBS volume to any EC2 instance, there's nothing further to discuss. When we do attach our volume to an instance, that's going to kick off another workflow. That volume attachment is going to pass the encrypted volume key to the EC2 instance. It also creates a key grant for that specific EC2 instance for that specific volume key for that volume only. The EC2 instance is going to send the encrypted volume key to KMS, and because of the grant, it has the permissions to decrypt it. KMS will decrypt the key and return that plaintext key back to the EC2 instance. From there, the EC2 instance will use that key to encrypt the data in transit, as well as EBS itself encrypting the data at rest. EBS volumes and AMIs created from that volume, as well as snapshots, are all encrypted using that same volume key. So now that we've talked about your options for encrypting your data at rest, it's time to talk about data encryption in transit. And the first type of data encryption in transit is going to be TLS. AWS has multiple services that support this. The first of these is CloudFront. By default, you can use HTTPS on any CloudFront distribution using the cloudfront.net certificate. If you'd like to use a custom or wildcard certificate from one of your own domains, you can absolutely bring those as long as they are provisioned using the AWS Certificate Manager or uploaded directly into IAM. They will be available in CloudFront. The Elastic Load Balancer has features for each of its 3 deployment types that allow for SSL or TLS listeners. The Classic Load Balancer, the Application Load Balancer, and the Network Load Balancer all support this. The API Gateway Service also supports TLS, and you can associate your certificate from ACM or IAM. Either of these will work with your API Gateway. Now, there is a 4th option, and that is to do an HTTPS GET of an object in S3. But there's a big exception here. This is only going to work if you use the basic URL that is available for every object that uses s3.amazonaws.com. It does not support custom domains at this time. So we've talked about data encryption in transit, but web services are not the only kind of services out there that can meet your compliance requirements. Database services in AWS also have an option for encrypting your data in transit. And we'll start with RDS. The RDS service allows you to apply an SSL certificate so that your database connections can be encrypted in transit. Redshift has a similar mechanism, but instead of using KMS, it uses Cloud HSM. The Neptune Graph Database supports encrypting your data in transit, and so does Elasticache, but only if you choose the Redis engine. There are other kinds of services that you might want your data to be encrypted in transit, and specifically for storage services, you have a couple of options. FSX for both Lustre and Windows support data encryption in transit, and in fact, it is the default for both services. For EFS, you have to put a little bit of extra work at the client side to enable that storage traffic encryption, but it too supports this feature. What if instead of encrypting your data in transit to individual services, you would like to encrypt all network transfers? You have a couple of options. First of these, and the most commonly chosen solution, is to work with a virtual private gateway and enable VPN on that gateway so that all traffic to and from the VPC that goes through that gateway is automatically encrypted. So this is going to use IPsec data encryption with the interactive key exchange. Direct Connect also allows you to use a VPN with IPsec, but this wasn't always the case. This is another example of where reading the documentation, staying up to date with the AWS blogs is going to be really important because Direct Connect now supports VPN traffic. A third option is to simply do it yourself. You can launch an EC2 instance into a VPC and install third-party VPN software like StrongSwan, or to use an off-the-shelf product like a Cisco Marketplace instance, and set up your own VPN. This is a way of being able to manage the entire VPN end-to-end at the customer side without relying on or delegating any of that responsibility to AWS. There are some other considerations with data encryption in transit, and you should look at the Service API endpoints for examples of this. All of the services support SSL or TLS, and in fact, some of them require it, like DynamoDB. You can enforce SSL as a transport method using IAM policy conditions, and we talked about those in an earlier lesson where you can set up a condition that ensures that SSL is being used or the request will be denied. However, SSL is not always the best choice. You should recognize where SSL can impact your performance. If you are uploading a number of objects in parallel to an S3 bucket, and each of them is using an HTTPS connection, the CPU overhead of encrypting all of those connections on the client side might have a large enough performance impact that you would consider performing your puts using a non-encrypted connection. Welcome to our final case study. And for this scenario, I wanted to walk through an implementation of end-to-end encryption on a traditional three-tier application infrastructure that involves a load balancer, a web app tier, and a database. And our considerations and the tasks we're going to need to make sure of is that we are encrypting all of our data in transit, we are encrypting all of our data at rest, and this includes backups, and we need to be able to apply compliance controls so that we know if existing configuration changes or if new resources are attempted to be created that are not in compliance. And so let's start with our infrastructure. We have our elastic load balancer tier in public subnets in a VPC located in their own security group. We have an auto-scaled group of EC2 instances in private subnets and some sort of RDS database deployment also in private subnets, not necessarily the same subnets as our application tier. And we'd like to make sure that we are encrypting everything in transit and at rest. So we start at the front. And when we create our listener for the elastic load balancer, whether it's an ALB, a classic load balancer, or a network load balancer, we will enable HTTPS and we will associate the SSL certificate with the load balancer itself. We will also configure our target group protocol. So let's assume we're using an application load balancer. We're going to configure our target group protocol also as HTTPS, and this is an important addition. This is going to allow us to encrypt the data transfer between the load balancer and the application servers themselves. But then how do we get an SSL certificate on the EC2 instances? We're going to use ACM We will upload our certificate that's been generated outside of AWS. We will use it on the load balancer, and then we will take the files that we have, the key, the chain file, and the certificate, and we will install those on the application servers so that they can listen over SSL as well, so that our requests from the client going through the load balancer will be encrypted all the way to the application tier. On the database tier, we will install self-signed certificates that have been generated using AWS Certificate Manager as a private CA, and we will configure TLS on the database so that all of our traffic between the application tier and the database tier will be encrypted in transit. We have one very slight risk that is exposed by this particular design, and that is we are going to perform a terminate and re-encrypt on the load balancer. There will be a very brief window of time where the traffic has to be in plain text between the SSL termination at the front end listener and when it encrypts it to send it to the back end. For purposes of this scenario, we are willing to accept this risk. Let's move on to encrypting our data at rest, and we have a couple of options here. Our EC2 instances are going to be launched using an encrypted AMI. This is a little bit of a process. In order to create an encrypted AMI, we have to create a snapshot of an existing OS, and then we have to encrypt it and then associate that with a new AMI, and only then can we launch with encrypted OS volumes. So that will ensure all of the data that is present on these EC2 instances will be encrypted at rest. We will use an encrypted file system for shared storage. This could be EFS, it could be FSX for Lustre, but in either case, we have the option of encrypting the file system itself so that all of the data at rest is encrypted. On the database tier, we're going to use TDE if we have Oracle or SQL Server as our database engine. That encrypts the database at the software layer. Regardless of the engine we use, we can also encrypt our data at the storage layer just using the regular RDS functionality. So at this point, we have all of our data in transit encrypted and all of our data at rest encrypted. Now we need to move on to the compliance task. When we create new resources in AWS, we have a number of ways that we can capture this activity and evaluate whether or not it is in compliance. For this particular scenario, we could choose an AWS config rule. We could even choose a CloudWatch event rule, but the config rule is the one that allows us to apply a little bit more logic on the creation and all of the metadata that's associated with the resource to make sure it meets all of our security requirements. Both of these are passive mechanisms. They will not prevent the activity from taking place. The best we can hope for is that we get notified quickly unless we configure some kind of automated remediation as part of the notification process. We've decided to go that route. So rather than sending an immediate notification, the AWS config rule, by identifying non-compliant resources, triggers a Lambda function with the information about the resource. The Lambda function does not care what purpose that resource needs to serve, only that it is out of compliance. And so the Lambda function's purpose will be to delete the resource. The final step for the Lambda function is to send a notification so that someone can see that notification and recognize that a non-compliant resource was created, but it has been destroyed according to the rules. We could choose to go with an active route to prevent non-compliant resources from being created in the first place. And we have a couple of ways to go about this. We could implement least privilege using AWS organizations and service control policies applied at the account level, as well as IAM permission boundaries applied at the user level. And we could even get the best of both worlds by applying both of these to the same account. It's not good enough to just block the request. We would also like a notification that somebody in the organization was attempting to create non-compliant resources. Since all of these actions are logged via CloudTrail, whether they are accepted or rejected, we could choose to have all of the rejected requests captured by a CloudWatch events rule, and then a notification sent to a distribution list so that they could review and potentially go back to the requesters and make sure that they are working according to the compliance rules. Welcome to our final question breakdown. For this scenario, I wanted to come up with something that allows you to test your knowledge of storage services in AWS, as well as dig a little bit deeper to make sure that you're also reading the documentation, even if you haven't tried something via the hands-on method. For regulatory reasons, your application data must be encrypted during all steps of every workflow, both in transit and at rest. The storage of data on the back end of the application is entirely file system based. Which storage options meet the requirement of in-transit and at-rest encryption? So let's look at our key terms. We clearly need to deal with encryption. We need to deal with in-transit, at-rest, but we only have choices that are file system based. That means services like S3 and Glacier are completely out of scope. So let's look through our 6 choices, remembering that we need to pick 2 along the way. EFS volume with an encrypted file system and an EFS mount helper on all clients. This sounds a little strange. You might not have heard of the EFS mount helper before. This is a good example of where reading the documentation can help you study for the exam. This does meet both requirements, and that EFS mount helper is a real thing, and it's exactly the step you need to be able to encrypt your data between an EC2 instance and an EFS volume in transit. Let's look at B. Instance store volumes with no extra configuration. Well, that would assume that there would be native encryption on instance store volumes, which there isn't. How about C? EBS volume, no extra configuration. That would be wonderful, right? If EBS volumes had a default server-side encryption enabled, but no. And since EBS volumes are not encrypted by default, this doesn't meet any of the requirements. How about D? EBS volume encryption enabled. That's interesting. I think this might actually be our second correct answer. It's going to allow us to perform data encryption in transit between EC2 and EBS, as well as at rest within the EBS storage system. So we've reached this point. We hit both of our correct answers. Let's look at the others because there's some interesting stuff, especially when we get to F. Let's look at E first. EFS volume, no extra configuration. It would be really nice if EFS did default encryption at rest and in transit, but it doesn't. If you need that, you can always choose FSX for Lustre or FSX for Windows. Let's look at our final answer. AWS Storage Gateway, File Gateway, no extra configuration. If you've read the documentation, you would recognize that the Storage Gateway is going to encrypt all data at rest, regardless of the deployment mode that you choose. And that does get us part of the way there. However, File Gateway encrypts data in transit between itself and S3, but it does not have any features for encrypting the data in transit between itself and the clients that are mounting the volumes. So this isn't going to be a correct answer either. And so our 2 correct answers are going to be A and D. Module 7, the final module, covers next steps toward certification. The single lesson in this module, Lesson 11, is full of resources and strategies for passing the exam. In Lesson 11, we will cover study strategies and different helpful resources that can increase your chances of achieving certification. So we've reached the end of our material, and now it's time to talk about where do you go from here? What types of activities should you perform from this point to help maximize your chances of passing the exam? Well, first, you can go straight to the AWS certification page for the Security Specialty Cert and download a PDF of sample questions. This is just a list of 10 questions that are representative of the topics and scenarios that you might find on the actual exam. And you should go through all 10 of these questions. You want to make sure that you know why the correct answer is correct. All the correct answers are listed at the end of the document, but you should be able to answer all of them with a high degree of confidence. You should also look through all 10 questions and know why the incorrect answers are incorrect. And this knowledge is every bit as important as being able to answer the question correctly in the first place. From this point, you should be able to recognize that you're going to have a couple gaps in your knowledge. Now it's time to study. In the next section, we're going to talk about the different tasks and documents that you're going to want to consume and perform in order to be able to improve your knowledge so that you can maximize your chances of achieving certification. For this study, you're going to want to look at specific subjects that you've missed in the sample questions. Next, you want to take advantage of the fact that AWS has multiple certifications, multiple exams out there, multiple sets of sample questions. And there are certain certifications that would be in scope from a security perspective. You have the SysOps Associate certification, you've got the Solutions Architect Associate certification, and you have the Solutions Architect Professional certification. Sample questions from any of these 3 exams will help you pick up background knowledge that will help you then with the Security Specialty Cert. Your next step is going to be to take the practice test. This is something you can do online in a browser from the comfort of your own home. You can do it at any time. You just have to pay the fee and take the exam. Now, with this practice test, it's going to be a smaller number of questions than the actual exam. You're going to be walking through these with the same mindset as you did with the sample questions. You need to know why the correct answer is correct, why the incorrect answer is incorrect, and again, recognize gaps in your knowledge. The practice test is not going to tell you which questions you got right. And so you're going to want to make sure that you've read them carefully. And you should be able to recognize when you're guessing and you're not sure exactly what that correct answer is, and note down the topics for these questions. Now, you're going to go back and do another set of study exercises, but this time you're going to be looking through question domains specifically rather than the broader subjects themselves. When you're confident that you can pass the real exam, it's time to go ahead and take it. So we've reached our final section of the course, and now it's time to talk about all of the extra information that you can go out and read and the tasks that you can go out and do on your own to help boost your knowledge before you go out and take the exam. And I wanted to start with a recommendation on white papers. But the first comment I got to make is that there's too many specific white papers to list. Your best bet is to go straight to the AWS main portals for documentation and white papers and look for anything that involves security. And there are a couple of different dashboards that I can give you URLs for where you can go straight to them and see the list of all the documents that are available. First one is documentation organized as security resources. And the second is all of the documentation organized around compliance. All of these documents are going to be in scope for the exam and can help you pick up background knowledge in areas where you might not be very strong because you haven't done a lot of it by hand. Next are a couple of outside documents that I think are appropriate for this particular certification. The first of these is the CIS Foundations Benchmark, but specifically for AWS. This is going to explain a lot of best practices and guidance from the CIS organization on how you can protect your account and protect the controls around your account so that you're notified when changes are made that take configuration or applications out of compliance. The other document we talked about earlier in the course, the NIST Special Publication 800-146. This is where you're going to learn about incident response and how to craft an incident response plan that is appropriate for a cloud-based deployment. Next, I'd like you to take advantage of a couple of AWS Quick Starts. There are a couple of dozen of these that are available in AWS, and they have documentation plus a CloudFormation template that you can launch into your own account with full instructions on how to install and configure it. The first of these is the CIS benchmark itself. This is a great little infrastructure to deploy for any account in AWS, regardless of whether you're studying for the certification or not. The second quick start is the ability to deploy Linux Bastion hosts. Understanding how to create a gateway into your system for management is going to walk you through a number of other required tasks like network security. And third, the quick start around modular and scalable VPC. The ability to create a VPC should be required knowledge for this certification, and this is going to help you polish those skills. Next, I've got a couple of slides of tasks that are just based on my own experience that I would recommend all of you go out and do in your own accounts because they're going to help take the topics that are more difficult and cement them in your brain so that it's easier to recognize on the exam and easier to answer questions rather than just memorizing documentation. First, deploy ADFS and configure SAML federation. You don't need to have an on-premises network to do this. You can simply deploy a VPC, deploy a Windows server, and set up Active Directory in ADFS, and then you can federate that against the same account where that VPC exists. Next, create multiple accounts using AWS organizations. This is a fantastic set of tasks that will teach you a lot about cross-account authentication, how organizations work, and how to use the command line to programmatically create and deploy account security. Next, implement SSL or TLS listeners on CloudFront and ELB. Because you can create certificates for free using ACM, this is going to be a zero-cost endeavor where you're going to learn a lot about the operations required to deploy and maintain SSL certs. Next, enable server-side encryption via KMS on CloudWatch logs. This is going to give you a great combination of console and command line experience. It will also give you experience with creating customer master keys, as well as the creation of the key policy that is attached to the CMK. Next, create a secure VPC with multiple egress points, and I cannot stress enough the importance of having a full body of knowledge around VPC creation, VPC security, and VPC operations. Look at all of the different egress points, the ways that you can get traffic out of the VPC, and how many security mechanisms apply to them. You are going to want to be able to do these in your sleep. Next, implement security compliance using config rules and Lambda functions. There's a lot of automation out there and Lambda function blueprints so that you don't have to generate a lot of custom code to be able to implement this. Next, create permission policies with conditions and test them. All of the conditions that we talked about, the if exists, the booleans, the IP addresses, you're going to want to understand exactly the ramifications those have on permission policies, whether it's IAM permissions or an S3 bucket policy or some other service that has resource-based policies. For our second set of tasks, let's start with creating CloudWatch events rules. These have a lot of really cool utility with the ability to match specific text and then send it to multiple targets simultaneously. Create an encrypted AMI. This is not necessarily a straightforward process. It's not something that you can do directly through the AWS console, and so it's going to hone your skills on the CLI in addition to improving your knowledge on operations around creating and managing the AMIs. Explore CloudTrail logs in CloudWatch. When you enable CloudTrail, you want to send those logs into CloudWatch logs so that you can view them directly. And using features like CloudWatch Logs Insights, you can query and really dive deep into these logs to understand what particular activities look like in these JSON events. Next, create and test cross-account permissions. This can be part of the same task where you're working with AWS organizations, or it might just be creating 2 accounts, one with each of your 2 email addresses, and playing around with cross-account permissions directly. Finally, configure and learn the AWS CLI. There are a lot of the operations that we've discussed over the length of this course that require the command line to be able to implement. You cannot do everything in the AWS console. And so working with the CLI is really going to help institutionalize that knowledge and make it easier for you to be able to recall when it comes time to take and pass the exam. For my final point, I'd like to talk a little bit about how to stay current in AWS. The AWS ecosystem is just exploding in terms of offerings, services, features, integration points, changes, improvements. Everything is happening so fast that it's really hard to stay up to date. And so there are a couple of places you can go to make sure that you're getting the latest and greatest as far as changes and updates and new deployments and so forth. The AWS News blog is a great general location to go to see anything that's happening in AWS that they have decided is newsworthy and worth a blog post. The AWS Security blog is going to be specific to the topics that we've discussed over the length of this course, so you're not going to be getting information about big data or machine learning or the latest processors that are available in EC2. It's going to be focused on the security topics. And the final place where you can stay up to date, and this is going to be almost like a fire hose of information, the What's New at AWS page. This is where all of the changes are posted, whether they are small or large, whether it is a blog post or a YouTube video or a reInvent announcement, they all show up here. And if you make sure that you're actually looking at the email address where you signed up for the root account in AWS, the What's New at AWS can be sent as a weekly digest, so you don't have to go out and specifically seek this page on a regular basis. Finally, stick with official sources. That is the only way that you're going to be absolutely sure that you are up to date. If you're reading somebody else's blog post or a trade magazine article or anything that is not posted directly by AWS, you run the risk of it becoming obsolete. And even within the AWS blogs, make sure that you're looking at the dates of the blog posts so that you recognize if it was 4 years ago that there might have been updates that superseded the topic of that blog. And with that, I just want to wish you the best of luck. Happy test taking. Congratulations! You've completed the AWS Certified Security Specialty Complete Video course. In this course, you've covered many of the prerequisites for the certification exam and spent time learning each of the question domains. You've reviewed question breakdowns in each question domain and walked through many case studies. You've completed quizzes as well as an entire practice test. I fully recommend going through this material more than once to help retain the harder topics and catch anything that you missed the first time around. When you are ready to take the exam, you can register for this online at aws.training. Best of luck on your certification.